Hello, everyone. Welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen, a professor in the Department of Chemistry and Biochemistry at Florida State University. I'm a photochemist slash photophysicist. I shine light on molecules and see what happens to that light energy, track it with ultra-fast spectroscopy, shine pulses of light and see what happens to that energy, whether it's making or breaking bonds, moving electrons, moving energy, and hopefully doing something useful with it. But more importantly, joining me today is Dr. Rachel Yohay. Rachel, if you wouldn't mind introducing yourself.
Hi, I am an associate professor at Florida State, and I am a experimental particle physicist. So I work on an experiment called the compact muon solenoid that's located at the Large Hadron Collider at CERN, which is Europe's premier particle physics lab. The LHC, the Large Hadron Collider, is the world's highest energy particle accelerator. By a good factor of about 13 or 14 beyond the previous highest energy particle accelerator. And we are smashing protons together and then detecting what comes out in order to learn about the fundamental building blocks of matter and about the fundamental forces.
Nice. What do you typically teach?
I've taught everything. Not everything, but a lot of things for undergrads. So I've taught the particle physics elective for undergraduates. That's probably my most advanced class. I'm currently teaching the mechanics and E&M, electricity and magnetism sequence for engineers. I've also done some teaching of that sequence for biosciences majors or health sciences majors. So the difference there is one is calculus based and one is algebra based. And I have taught also intro astronomy for non-scientists. Which is really fun.
Casual astronomer, yeah.
Yeah, like really, really fun to teach.
Students are more excited in that, right? Like, that's unfortunate.
Yeah, I've been told though that like, it's too mathy,
Math is the fun part of the universe, ladies and gentlemen. All right, equally important, what game are we starting with?
We are playing a game called Good Job. And so I'm not a huge gamer, but the conceit of this game is that your dad owns the company and he's built this wonderful office building with all these happy office workers. I just got to pay attention here. Route the internet cable. Okay, I got to bring the news cable to the switch. It's over in another location. Okay, so your dad runs the company, and because you're his kid, you obviously, so you're this guy or girl with your crown, you obviously get a job at the company. But you're horrible at working. And so, you are given a series of progressively harder tasks that, don't really require formal education, but just require some attention to detail. And you just stink at them, but you're going to try to do the job. And when you do it, you've done a good job. So I am like this guy when it comes to video games in that I'm not really very good at them. So it kind of works. So now I know I have to move this cable, but the question is, where did the thing just tell me to move it to? Here. I'm going to just trace out the path of where I think I have to go. So like, for example, these double doors, they don't open unless I plug them in. Then I gotta like break all these boxes. Okay, but now at least I can. Thankfully, it doesn't make you go around the like cable. Like if I had to trip on that, I'd feel really stupid.
Oh, you'd have to order of operations.
Where did he? Yeah, I'm trying to think. Where did I? Oh, that one just opens.
So does this game speak to the scientist in you in terms of troubleshooting and like what about it?
Here it is.
I mean, it's funny at the very least.
These poor people that have to pee really bad. I guess I have to go this way.
That's how they block the path.
Yeah, exactly.
That's amazing.
Oh, but then I gotta go through here, and then through here. So it speaks to me as I guess, yes, I like the puzzle aspect. Okay, so this is what I'm trying to do. Oh my God, how am I going to do this? Yeah, I like the puzzle aspect. They give you, like I suppose we think of ourselves giving our graduate students, you know, directions, or undergraduates. Okay, here's what you have to do. Now go do it. And it takes the newbie some time to kind of get used to the tenor of the instructions and kind of the gist of what they're trying to do. But through hard work and a little bit of hand-eye coordination, attention to detail, self-awareness, in principle, it is possible to do the job. Let's see. Okay, so I got to get it through here.
Maximinimus, starting out with a hard one. Are you ready for this?
Okay, I'm playing the game, so I can't even read it. I'll
tell you. So, what's your best guess? Is it dark matter or modified gravity?
Oh, dark matter or Mond?
If you had to put money on it,
oh no,
how much would you put?
Wait, what am I supposed to do now? I can't take it all that way. I guess I have to bring the cable, not just... I have to think about this. I think it's still I think it's a particle. Because, well, a lot of things work out nicely if it's a particle, having to do with early universe cosmology. The role that dark matter plays in seeding the structure of galaxies, and it doesn't, it holds them together and doesn't blow apart due to radiation pressure the way, you know, because it doesn't radiate photons the way ordinary matter does, or anything else the way ordinary matter does. It's true that with like the James, so this isn't my area of expertise, but with the Webb observations that kind of throw a little bit of the early galaxy formation stuff into some question, it's under discussion, but still, I don't think we have, I'm trying to think of an evidence of modified gravity. I mean, beyond Einstein modifying Newton. But, you know, we don't have evidence of modified gravity, at least at small scales, nor, I mean, so far, nor at the largest scales. So it still seems likely it's a particle, and why we haven't found it could be the so-called, you know, lamplight problem or whatever. Like you kind of only look for your keys where the lamp is shining.
Yeah.
So what are you missing?
Yeah, that's fun.
Yeah.
Laura, you are right on time. Well, welcome back. Thank you for joining us. Did I miss the drink of choice? No, you did not. We are drinking from Cigar City. What do we say? Guayabera Citrus Pale Ale. Citra Pale Ale. So, yeah. There, green screen.
Right.
Oh, my bad. But yeah, you guys can see the link right there. This is from Tampa. So, any rationale for this choice? It's just one of your favorites.
Yes, I like. So they have a kind of a more high gravity version of this called Highlight that I really like, and this is sort of the one that I was like, I have to drive over here. I'm not gonna take the.
It's the lighter one.
Yep.
But I have Highlight in the fridge if you want it. So we'll see where this game takes us.
I'm already stuck because I can't get this thing as far as I need to. If anyone out there knows what I'm supposed to do, can I, like, do I move the other switch
good
over
job.
here?
Feel free to coach us through it.
Yeah.
Rachel's playing.
Otherwise, I'll have to switch to something like really, you know, really low level.
Yeah, thinking while talking. Misadventures in Astro, welcome back. Hello, hello. Thank you for joining us. Wedge the door open with something is the suggestion.
Wrench the door open.
I think the one you tried to get you can wedge that open with a box or something.
This one?
Yeah. It's the suggestion from Maximinimus. Wants to know about dark matter versus modified gravity and wedging door open.
Wedging the door open. Okay, I can
Misadventures
try that.
in Astro. How are the doctors tonight? I'm doing well. First week and a half of class is done. So are you Monday, Wednesday, Friday, or are you Tuesday, Thursday?
I teach Tuesday, Thursday, and the
Okay.
class is it's a 5 credit hour class. So there's other members of the instructional team who teach Monday and Wednesday, like so a lab section.
Ah, I see.
I think
So you've had 3 class periods so far then. For me, it's
yeah.
Yeah, what are we at? 4 down, 34 lectures to go. So we're making progress. We're 10% the way through the semester already, which is crazy. If you do the per lecture breakdown. Time flies when you're having fun. Speaking of which, it has been a little over 4 years since you've been on the stream, which is kind of crazy. It feels like a lifetime.
Yeah.
I mean, and it literally is, because your kid is about that age. I think you came on right after you had, or a couple months in or something like that.
Yeah, so 4 years, so 2021. Yes, Harriet would have been born. Our daughter would have been born late 2020. So yeah.
Yeah. That's crazy. So 6-7 months after that. But yeah, welcome back. Thank you for joining us. I imagine a lot has changed in life, but we're going to start with, and Old Man Felonious, I see your question. We'll get back to it, but we're going to open with our classic question we ask every single guest. And what we really, most students think that we were just destined for this job, and we all know that's not true, right? There are a lot of turns and forks in the road and decisions along the way that narrowed us down from all of sciences to physics to particle physics. And so what were those milestones for you? What events on the path, from, high school to college to grad to postdoc that got you to where you are today?
All right, I'm just gonna say it'll be hard to answer while I'm playing, but let me think. So I came into college thinking I would major in computer science, and I had to take physics in my freshman year as part of the core, and I loved it. I always liked physics in high school, so that's when I decided I was just gonna declare physics as a major because I, really just wanted to know more. I remember being interested in particle physics even at that time because, so let's see, I would have taken this class in late 2000, maybe early 2003. The LHC was under construction, and I recall my professor showing like a picture of the empty tunnel and maybe discussing a little bit about what the LHC would do when it was constructed, and it got me very excited. So then, you major in physics, go to grad school. I will admit, at the time I applied to grad school, I was totally interested in LHC physics. I knew that's what I wanted to do. So here's maybe, milestone number 1. I wasn't an official, CERN has a summer student program for European summer students, and they're excellent, and it's a really great cohort of people, and you get to do a project there. I was not an official summer student, but I was like an American who happened to be there doing a project, unofficially as a summer student. And I really enjoyed that experience. It was both, intellectually interesting, socially fun. And so I knew I wanted to go to grad school, got into grad school, knew I wanted to get to CERN. And then kind of like it's probably similar for you. You go through, you're moderately good at something. You get to be there during, the Higgs discovery, some big moment. And then you can see kind of what the future path will be, and you just apply for positions and try to get there. So it can feel a little bit, now I remember. It can feel a little bit path dependent or, determined once you get there. But, okay. Yes, now you can all go to the bathroom. Yes, I pick you up.
So I'm curious, how did you get into that summer program?
I didn't have to get in because I was just working. Oh, no.
Dejected.
Can I move? Oh, no, it almost makes it. No, there's got to be. No, put it down. This can't move. It wasn't a special program that I got into. I was working with a faculty member who was collaborating on the CMS experiment. At the time it was building the CMS tracker, he had just joined the experiment, and he had a couple of summer students, and he had some money to bring us out to CERN, and that's how we ended up going.
I mean, that's pretty cool that he brought undergrads out to CERN.
Yes.
That's not a normal experience, presumably.
No, we were very, very lucky to be able to go. I think oh yeah, I got to move these people. See, look at this. This gets you thinking about the precision. I have to, sorry, guy. You just can't work here. You're going to have to go.
All right.
Because I need just a teeny bit more length.
Oh, that's fun.
Yes.
So Old Man Felonius has a specific one. CMS question mark? Actually, just reading your bio. NCAP calorimeter for the HL-LHC.
Oh, boy.
Nice reading your bio online. Intertrack strip detector portion on Atlas here. So he actually works on Atlas.
Oh.
Kind of cool.
Okay.
So yeah.
Someone on the stream is on Atlas?
Yeah. Old Man Felonius. If you guys haven't, he's a fellow streamer. You guys should check him out right here. Talks about a bunch of stuff on stream, but also being a physicist / engineer, if I'm remembering correctly. But yeah. Oh, here we go. I found his bio. Doing part-time masters in electrical and computer engineering, I work on the Atlas experiment and the new detector technologies, DRD3, at CERN on the side.
Oh, yeah. Okay.
It's small world.
Yeah, that's a really small world. Yes.
That's pretty fun. Working on that while doing a master's and streaming every once in a while. You guys should check out Old Man Felonius' stream.
Welcome. We won't hold it against you that you're on Atlas.
What's wrong with Atlas? Oh, there you go.
Yeah.
Oh, that was it.
Yeah. So that was like me completing this in the amount of time, an Atlas person would know. I'm kidding. No, Atlas there are two big general purpose experiments at the LHC. And by general purpose, they are designed to detect all kinds of particles. They are not designed with a specific final state in mind. There are two others that are very specific. And Atlas is the other big one. That means it also played a role in the Higgs boson discovery. It also has made a lot of the cool recent flagship measurements, measuring the Higgs, the strength that the Higgs interacts with other particles. But,
fun.
CMS, they have slightly different designs, and it definitely gets a little bit into the, inside baseball, like which is better, which is worse.
Yeah.
But I could say some parts are better for some things.
But you're not biased.
Mm-hmm. I'll say, as someone who, as a graduate student, I worked a lot on what was supposed to be the, sexiest, but like, most precise, super awesome part of CMS, which is its calorimeter for measuring the energy of photons and electrons. And it's this beautiful thing. It's made of 75,000 individually grown lead glass crystals.
Jeez.
So it's lead. You think of lead, totally clear, completely clear. These inorganic crystal scintillator, you know about this stuff, right?
Yeah.
So they light up when particles come in and interact due to the, quantum mechanics of the molecular states and stuff. And it was supposed to have, an incredibly, world-beating, tiny, really, really high precision energy resolution to allow the discovery of the Higgs decay to photons with incredible precision and an estimate of the mass. Now, it does work pretty well, but it turned out to be incredibly tricky to calibrate with these individual crystals, and they're all kind of aging at different rates, and they were made at different factories. And so I think in the end, Atlas's electromagnetic calorimeter, despite, not being as, pretty or whatever, or as highly touted at the time, performed just as well or maybe even a little better in terms of the calibration precision because it was much simpler to work with. So there you go.
That is intriguing. So shout out to Atlas.
CMS's magnet is much stronger, so we do better with particle, certain kinds of final states that require strong bending.
That's awesome. Man, how devastating is that, though? Somebody worked for, decades to get that system up and running. And it's like, oh, it's hard to calibrate. So sorry.
And it's not like people didn't try. There were a lot of smart people working on it. And we still have it. We're replacing part of it. So that's the new NCAP calorimeter. So those crystals in the parts of the detector that just because of where they're located, they're more right directly in, sort of in the path of the beam, they will be black. Like they won't make it to the next phase of the LHC, which is called the HLLHC. They're already kind of like turning yellowish and brown. And so they're going to be replaced, and that's something that I'm working on. It's a totally different technology for the replacement.
Oh. For those of you that didn't see, Rachel got a B. That's good enough.
I totally, yeah, this game is all about, you said mediocre gameplay.
Yeah.
This game like celebrates mediocre gameplay.
Mediocre office employee is what we got going on here, ladies and gentlemen.
Yeah.
Oh, man. That's fun. All right, I'm going to catch up. Oh, we got shots fired. Maximinimus, the CMS eCal was more overrated than Alabama football.
Oh, my God.
Or no, it was a question. Are they more overrated than Alabama?
Is it more overrated?
Yeah.
Wait, I got to pay attention to this. I got to do something. Okay.
Oh, this is the instructions?
These are the instructions.
All right,
So, okay.
we'll get back to Alabama
I got to
football.
gather workers.
Oof. Shots fired.
I got to get them all in one place. All right. Is it more overrated than Alabama football?
Well, that's the thing. Is FSU underrated or is Alabama overrated? And we don't get that answer till
Right.
a couple weeks.
Right. So
It's all relative. But fun factoid. So Lori in the chat right now, she was at the Alabama game.
Okay.
She was in the president's box for the
Ooh.
game. And so she got the FSU Max Caraway Employee of the Year, and part of that reward was getting a president's box seat. So
Congratulations.
Lori, I hope you enjoyed that game. That was pretty. Did you watch it?
We watched it on TV. Yeah.
That's awesome.
That was really exciting. Oh, and so I have a new postdoctoral scholar who is based at CERN, and he knows nothing about football and doesn't really, but I told him on our meeting on Tuesday, hey, your employer had a pretty big weekend beating Alabama.
Your employer.
And he said, and he laughed and he said, well, I know the University of Alabama they also work on the CMS experiment and also on this NCAP calorimeter replacement. So I'm going to go find the guy I know and like talk shit to him.
We earned it, damn it. We teach those students. No, we don't. Have you ever had a football player in your class? Maybe a strong.
I don't think I've had a football player. I've had like runners and I had a
tennis players,
I've had a
volleyball
cheerleader.
players. Yeah.
I've had that kind of thing. I have not had a football player. I feel like I'd know. It would be clear.
I learned from one of my colleagues, if you have like a softball or baseball player, they can potentially nominate you to throw out the first pitch of the game.
Oh,
I have not had that happen yet.
that's cool.
I won't take that personally, but if any softball players or baseball players are watching,
Check it out. I got a new hat.
love to do it. No more Crown. No more Prince of the Office.
How do we suppose I get this guy to get off his ass and move to this other conference room?
Cuddle Puppy wants to know, how many more years until you successfully create a black hole that swallows the solar system to destroy all local life?
I think probably more than 2, but maybe less than.
There are much worse pressing problems, particularly in the United States right now. But anyway.
I think that it is not going to happen.
But people have done the math on this.
I think,
It's
yeah.
on zero.
I can't tell you specifically. It's probably like, greater than the age of or maybe, one that would destroy the solar system, but created at the LHC. Well, that's, I think, never going to happen. I mean, the LHC will run for, its current run will end in about 8 months, maybe 10 months.
Oh, wow.
Yeah, and then we will shut down and then start the high luminosity LHC, which will have 5 to 7-ish times brighter beams, and that'll run 10 years. And we're not going to create a black hole in 10 years. It would be, it'd be much, much, much longer than that. So the LHC won't create one. Like nature could create one, but I don't think anything is in danger of that near our solar system because we're not near any heavy, high mass stars that are going to collide into each other. That's the way the black holes we know about are made.
So Cuddle Puppy, congratulations, you get to survive, or I'm sorry you get to survive, depending on your outlook on,
right.
on whether
right.
you wanted a black hole to suck in everything. But this is something that was genuinely discussed at some point, right? Like somebody had to do the math and make sure.
Yes, yes. And I think one of the arguments that was made is that far higher energy cosmic rays are, raining down on Earth, than we could ever make in the LHC. So if it hasn't happened already, it's probably not going to happen anytime soon.
Cuddle puppy. I did MMA. I'll let you throw out the ceremonial first punch. Who do you get to... Oh man, only if I get to punch who's the main CEO of MMA. Don't remember his name, but they're going to do a fight at the White House because that makes sense.
Wait, really?
Yeah, that is, the rumor is.
Is it? Well, one of the people. Oh no, McMahon is not MMA. That's WWF or whatever, but is in sort of a big donor and stuff, right?
Yeah, and his wife is running the Department of Education.
Right. Right.
Leoz000 Fermi, welcome. Thank you for joining us. First time chat. Click the follow button if you're not following. Get notifications every 2 weeks about streams. But yeah, thank you for joining us. Our guest today is Dr. Rachel Yohay. Rachel is an expert in high energy particle physics, in particularly Large Hadron Collider and the CMS detection. So yeah, she's happy to talk about any of that while playing Good Job, which is a puzzle solving game where you destroy an office.
I'm already confused how I'm supposed to get these guys moving.
Yeah, and if anyone wants to backseat game, we are not opposed to that.
Not opposed at all.
Yeah. Old Man Thelonious has a follow-up. CMS and Atlas are different designs, which is really helpful when declaring discovery because they do their measurements differently. If they both see it, there's more confidence. That's fun. That's a good perspective.
Yes. That's when the LHC was constructed, and it was kind of known even then, because of the energy that would be accessed, that there would be something exciting to be discovered. Because of previous measurements that indicated that there either had to be a Higgs boson or something like it, something that helped to control, the rate of sort of there's some measurements of things we already knew about that theory would predict would just go to infinity, and there aren't really infinities, right? And so unless there was some new particle like the Higgs, and so it was kind of known that it would be there. And so in the construction, it was always understood there has to be 2 experiments because it's too important to leave this to just one experiment. And what if it's not conclusive? What if something goes wrong and it doesn't get to the results in time? It's also good to have 2 of them competing with each other, friendly competing with each other, because it helps with the sort of social aspect of science or the meta science of like, can we trust this result? Can we believe this? And I think having 2 experiments helps a lot with that.
All right, Maximinimus has advice here. Sliding doors to the southwest of the guy in the green vest.
Sliding doors.
Many guys in the green vest. It says, use the plug on the other side of those sliding doors to set up a slingshot.
Slingshot.
That is amazing.
Slingshot.
That's awesome.
What?
Sliding doors to the southwest of the guy in the green vest.
First, I got to open them. How do I put my stupid thing down? There we go. This is what opens the door.
Let you follow through.
And yeah, it's fun to
gather the workers is the goal.
Okay. Oh.
Maximinimus, thank you. That is amazing.
Except
non-dairy neutrino, welcome back. Hey everyone, it's been a while. I saw physics, so I had to stop by. That's awesome. Yeah, we're talking physics, not necessarily neutrinos. You don't deal with neutrinos too much, do you?
No. So neutrinos escape our detector completely undetected. They are produced at relatively incredibly low rate.
Oh, they are produced though.
They're definitely produced. So when we produce W bosons, which are heavy fundamental particles. They're as heavy as a heavy nucleus. So if you think of a proton weighs in our units 1 giga electron volt, and a W boson weighs 80 of those. And it's one of the particles related to the Higgs theory. No, put that down. When those decay, many of the ways they decay are to neutrinos, to something we can see and a neutrino. And so we infer the presence of a W boson by actually seeing kind of the missing momentum or missing energy due to the neutrino,
The loss.
which is totally different than dedicated neutrino detectors, where they're huge and they either are detecting neutrinos produced at a high rate because they're coming from a dedicated beam of decaying particles, or from a reactor, like a reactor neutrinos. And they have huge detectors, and the rates have to be high. The cross-section, the amount of material presented to the neutrinos has to be high so that you're lucky enough that you get an interaction.
And so, do you like the Japanese detector, the Super Kamiokande? That's the neutrino detector, if I remember correctly.
Yeah.
Do they see it when you guys turn on the LHC? Like, can they tell when noise increases?
No, because we don't produce enough neutrinos. By the time, the chance that the ones we produce, you're right, they do escape undetected, but the chance that they happen to hit that detector, like if you think about the amount of material that presents, across the world to this sort of relatively weak luminosity, weak brightness of neutrino production, it's so tiny that they would never see it. That would be cool, though.
They're just like, oh man, it's on again.
Can I push him?
I like it. So, Maximinimus, open the door to the conference room, and he will walk to it if he can see it. Interesting. Maximinimus, I'm going to assume you played this before.
Yeah.
Not just...
Thank you, Maximinimus. So there's like one other person on Earth who...
I don't know. This looks like fun. I might have to pick this one up.
Yeah. Do you play while we... No, you...
No, I don't.
You host.
Actually, that's not... I will be the guest on... Let me see. On November 5th, I'm the guest. So I run the admissions to the chemistry department.
Okay.
And so we do a graduate admissions Q&A. And so I'm the guest, and our associate chair of graduate studies is the host. So yeah, I'll get to play, and yeah, maybe play some NHLPA 93. Those of you guys that have been following the endeavor, one of our previous guests played NHL, and so I played it, and I got the world record for 5 goals and 10 goals speedrunning NHLPA 93, and somebody took it back literally yesterday. So I've lost my world record. I'm now the runner-up in that, so I might have to play that one again when I'm on stream. But...
Does that have like the real teams and logos and stuff?
No, not the original one, not the NHLPA one, because it's Players Association. The NHL wouldn't approve it because they have fighting in the game. And so it wasn't until a year later that the NHL approved.
I grew up on Long Island in New York, and there was a period when the Islanders had these like horrible, do you remember the fish sticks logo? And I was just like wondering
if it was in that game.
Yeah. All right, I'm going to try to
not in the
slingshot him
93
again.
one, maybe in the 94. All right. Leoz, we'll say Leoz. What's the current hypothesis on whether dark matter is real or not in terms of astronomical importance? Dark matter. So we talked earlier about it potentially being a particle.
I think it's important. Obviously, there's not much explanation for the rotation curves of galaxies without dark matter, because there just doesn't appear to be the right amount of visible matter to explain how fast they're moving. That's one thing. So I don't know how that works out without dark matter. Maybe modified gravity comes in somewhere there. That feels a little more like less Occam's razor, I guess, than that there's a particle. Or less Occam's razor. And it also is supposed to play an important role in early universe cosmology and in the formation of large-scale structure. The idea that, just after the Big Bang, the universe is extremely hot and dense and condensed, and there are, we're kind of in a plasma or something of, particle interactions at incredibly high energies that we no longer access, except in the lab anymore. And that the something that interacts only gravitationally, but not electromagnetically or weakly. The weak force is another one of the important forces that's responsible for radioactivity, or strongly, which is the force responsible for why the nucleus stays together. That if such a particle can seed, the structures that end up being galaxies, that end up being large things eventually, as the universe cools and time goes on past the Big Bang. And so without dark matter, I think it's without something like that, I don't know how, again, not my area of expertise exactly, but how you would get any clumpiness, like any structure that we see, and why the universe wouldn't be much more boring and sort of like thermalized and uniform than the one that we actually see. I guess it can happen without particle dark matter, or it may be that dark matter is there, it is a particle, it is only gravitationally interacting, and therefore we'll never detect it. Right? I think all of these models of particle dark matter assume it has some incredibly weak, or feeble coupling to something we can see either through the weak force or the strong force, or there are some ideas about maybe it's a portal. The Higgs boson could be a portal to like a hidden sector that we don't see, but there has to be, again, the sort of the bias of the experimenter. We always concoct models where there's some way that we can see it. But if it is just gravitationally interacting,
it's hard to detect.
Then it's just astronomy. Yeah, exactly. It would be very, very hard to detect.
Huh. That's interesting. Non-dairy neutrino as a follow-up to that. I'd put my money on dark matter, but modified Newtonian dynamics, MOND, theories are fun to think about.
Yeah. Does any particular like idea that there's extra dimensions, or like does he or she have any idea? I don't know. Oh, can we get through the door?
You got to push them.
Try. My gosh, this is like having children. I should know this better. Come on, go. You can do it.
Non-dairy neutrino.
He did it.
I've always loved the model that dark matter is just a bunch of primordial black holes flying around. That is interesting.
Yeah.
That's a lot.
Yeah. So again, something just gravitationally interacting. Not a particle, a primordial black hole. So like a gravitational singularity, but not a particle like a graviton, not like a particle with spin or something. Do not know.
All right, non-dairy neutrino. Leo's Fermi has a follow-up. The Minos detector is thousands of tons of iron to detect neutrinos. I mean, it's crazy. You just need a huge absorption path, right? The absorption cross-section is so small.
Yeah, the Minos. Go through. Come on. Sorry. Yeah, so these neutrino detectors have to be very large to have a large cross-section. But very... I'm surprised it's iron, because normally there's something like water, because it's a detector. It presents a large interaction cross-section, and the decay product, or not the decay products, but the
radiation.
can also be seen. So like with you mentioned Cherenkov radiation. In a water detector, the big new one that's being built at Fermilab, Dune, will have liquid argon, which has a bigger, is very dense and presents a lot of interaction cross-section. And then a lot has been learned about all the nuclear interactions in argon. And so the idea is you can detect the particles as well. Minos is... in the Sudan mine.
Our steel scintillator.
Oh, a sampling calorimeter. Okay, so that's so I see. So that's actually kind of a similar idea to the kind of calorimeter that we are building for. I mean, that exists in a lot of particle physics experiments, but that currently exists in part of the CMS detector, and that we're adding more of for the NCAP upgrade project we're working on. You can do it. Come on. He did it. Okay, I got one. I got one in there. Do I have to get him seated? Somehow.
No, it gave you 4 of 8 workers.
Oh, good. There were 3. All right. Well, it took me 20 minutes to get one guy in there. So it really is just like trying to get our kids
that's
to do anything.
So what do you think the speed run record on this game is? Fastest someone is beaten. Good job.
I'm not like... I bet if you knew and you had practiced, you could do these puzzles in a minute. There are many more of them, but you have to kind of already know what you're doing, which I guess is how you do the speed run. All right, let's see if I can get this guy in there.
So the answer is 1 hour and 8 minutes.
To do the whole game?
Yep. Wow. So there's a whole lot of levels.
Yeah, there's like, 8 floors of this building.
Something? No, not 100. Oh, that's the room number. Okay.
Oh, I gotta...
So which one are you in? Are you accounting?
I'm in, I'm on the first floor. Yeah, I think so. How do I open the door here?
So finance 101.
Oh, right. I got
legal. Finance 102 accounting. I think you beat that. This is 103 taxes.
No.
But the answer for any given level is 17 seconds, 14 seconds, 57 seconds, 37 seconds. They are not messing around. And cumulatively, they end up.
Oh, that was fun. You can break the window. I just learned that. I didn't know you could.
Oh, how much money did you get for that?
I'm not sure, but this is like at Fermilab, which is the office tower. Well, Fermilab is the lab. It's the United States particle physics lab, named after Fermi, and it was started by, or conceived and like had a large hand in building it by Robert Wilson, who's a scientist, experimentalist, accelerator physicist in the 50s, 60s. And then, it came online in the 70s, I want to say, early 70s, maybe late 60s. And so the main tower there where people work is called Wilson Hall. And I learned from a colleague who, when I was a grad student, who's quite a bit older, is probably long retired by now, who said, oh yeah, like at that time he was such a big hippie, and they had this idea that, we don't need like offices in Wilson Hall. We're just going to sit on beanbag chairs and, talk about physics or whatever.
Awesome.
But even the hippies were like, well, eventually we have to actually like do some calculations and program some things. And so we do need offices. So they put up these like clear glass partition things for all the offices, so you can like, I don't know, it seems kind of you don't really get much privacy, right? You can see inside, but now I'm thinking, oh yeah, if I could just slingshot something through the office of someone I want to get the attention of. But now that I've done that, I can actually open this other door.
That is amazing. You're gonna see me hanging out in my beanbag all day.
Come on, guy. You can do it. You got to go to work.
All right.
No,
Man, we'll do non-dairy neutrinos question, then we should do a prediction, because it's about time. Non-dairy neutrino wants to know, I'm curious if you work with, or at least in general, actually, how much computer power is necessary to process, in a reasonable time, all the data produced from even a single experiment. I've heard it's near petabytes. We had a prediction on this last time, didn't we? Like
we
the total
did.
Amount?
Yeah,
I don't remember what it was.
I think we did. How much computing power to process? It was from a single event?
Yeah, yep. So how much data is generated from a single experiment?
A single event.
I don't know what experiment means in this context, but...
Yeah, so if you count up all of the data collected by the experiment or processed, even in 1 year, I think it's order of a petabyte or something. I remember, and we could probably do, when I was a student, like really looking at events, like looping through them, you'd have these files and you knew like, there are so many events in this file, and you open the file and it's got all the information about the momenta and energy and all kinds of other derived quantities from the reconstructed particles. And I remember this heuristic of about maybe 1 megabyte per event of data is what we ended up saving slash deriving, for the user to use. I think it's even less now because we've gone to a huge amount of compression to try to allow people to do more bespoke algorithms on their own bespoke algorithms to analyze the data. ML obviously has taken over, and to process more data more quickly. But yeah, the raw data is definitely like petabytes per year.
Wow. Nandaria, as a follow-up, is that data publicly available?
Oh, good question. The vast majority of it is not publicly available. So unlike in astronomy, unlike in like NASA-funded science, we are open science in the sense that our papers are typically, if not exclusively, published in open access journals that don't really have subscription fees. We put a lot of our papers on preprint servers. But the raw data is not publicly available. There is a small sliver of old raw data that has been made open for analysis, and I know there's a fairly prominent researcher, a theoretical researcher, I want to say at MIT, I think it's Jesse Thaler, for anyone who knows, I might be pronouncing it wrong, but who actually like wrote a paper and like did a project with the open data of CMS and like awesome. Was like, yeah, this really is as hard to analyze as they told us it would be.
I was going to say, you're not going to have a lot of armchair scientists doing something useful with that, right?
Even when NASA makes a picture, or the raw, like it's been, so many algorithms have been run on it to like, sharpen the image, maybe add, if it's a really composite image of things taken in different wavelength bands, to bring it together to like, screen out the Starlink satellites, and all this stuff they have to do to get it to even look usable for a non-expert in that experiment to do something with. And I think data are made even for experts. They have a much bigger history of making the data openly available. In our experiment, there is so much processing that has to be done to the raw data to get anything remotely recognizable and usable to a non-expert that it is not typically done. That doesn't mean we shouldn't, move toward that, but we don't tend to do it. Something that's kind of in between is we try to make results available in more, and kind of like the broad strokes of how we did our analyses available for sort of like reanalysis framework. So the idea is like a theorist comes along in 5 years with like a new model and wants to reanalyze at least the high level result, of an experiment or an analysis that a CMS or Atlas scientist did. They can try to take the measurement that was made or the search that was done, and knowing what cuts were applied on the momenta of the particles and the mass and all that, they can try to figure out their own, how would it exclude, what does it say about their model? So we have a baby version of it, but it's not nearly as good as for astronomy.
Yeah. Leoz has a follow-up. It's not available because it's secret. It's not available because it's huge. That's a lot of data.
That's another thing.
Yeah, who's going to download for the next 20 years of their life?
Leo's
000 Fermi.
Me, yep. Tevatron, floor 12, big pendulum. It is also very large. It is a lot of data. It's a full-time, department at CERN to manage, access to archiving of, you know, all of this data, I can only imagine, you know, also maintaining it as sort of an open resource. It also takes, you know, resources and like human resources that maybe don't exist. So.
Yeah. And yeah, what's the likelihood that a casual armchair scientist or benchtop scientist is going to come up with something from that? Like, or are they just going to see Jesus in toast? Because, like, there's going to be patterns in the data somehow, right?
You know, yeah, right. I think something you might, so something that gets done, I don't know if it's exactly open data, but the new calorimeter that we are constructing for HLLHC is going to have far more channels than previous ones. So I talked about this lead glass calorimeter. It had 75,000 channels. The new one will have 6 million. And that's part of the design. And so it's going to have an enormous, the way it works is to have, it's called the high granularity calorimeter. And so it basically has enormous, you know, you're counting, you know, charge tracks going through every one of these little cells that's, you know, about the size of my thumbnail. And because it will have so much, it will create so much data, it collects so much data, and it's 40, you know, each side is 47 layers, you know, of this highly segmented thing. A lot of people who are interested in, you know, machine learning or AI reconstruction algorithms want access to that data set, or we don't have the data set yet, we haven't built it, but to simulations of it to try to play with new ideas in fast reconstruction or end-to-end machine learned reconstruction of tau lepton decays or jets or some kind of new physics model of jets or something. And so we've had, I think there's like a scientific or computational interest in seeing at the moment, like simulated versions of what this data would look like. So people, kind of CS minded people, can play with it. And then eventually like the real data. But and you know, we've had some discussions in our collaboration a little bit about how much we should encourage this, how much we should kind of levy a tax for it. Like, hey, you want to like use the simulation, like come help us build the detector too, you know, or how much we should just be, this is good and like let's just let it happen. So
all right, we're almost an hour in. We should pick a prediction. Which one do you want to do?
Let's do this third one.
Third one. All right, ladies and gentlemen, we're going to pop up a prediction right now. If you're not following us, click the follow button. You'll get 300 standard internet units that you can gamble on this question. Unlike most streams on Twitch, we don't use our predictions for gaming questions like, will Rachel beat this in under 35 minutes? Instead, we ask questions to you guys. We have science questions related to the expertise of our guests. I force all of them to write questions, 6 or 7 of them, and we get through, I don't know, 5 during the stream. But yeah, we're going to put the question to you. Note you're on Ask a Scientist Gaming Honor Policy. You can't look up the answer. Just whatever you've learned from Rachel playing a good job versus what we've talked about so far to answer these questions. And so here's a question for you guys. The top quark is as heavy as 340 electrons or 340,000 electrons. Electrons are obviously small, but so are quarks. So question is, how much smaller is a quark than an electron? Is it 340 electrons? Is it 340,000 electrons? Put your predictions in now based on your degree of confidence. Do more or less standard internet units. Again, if you're not following us, click the follow button. You will get more points to gamble on this question. Is there anything? That's a pretty straightforward question.
Yep.
All right, we will leave it at that. All right, do you want to keep playing? We're at about 1 hour in.
I'm going to find the 8th worker.
You have to, right? It's just moral imperative.
Moral imperative, and then I'm going to switch to something less.
Less intensive.
I mean, this is just too, yeah. I mean, I want to say like, oh, I just, you know, I worked so hard all day thinking that I just can't even manage, but that's not true.
Oh, man.
I'm just terrible at this game.
I spent all day making PowerPoints.
Yeah, right.
So,
Me too.
So
Got to give one tomorrow, and then also teaching.
for class.
Yeah, one I have to give a sort of a update to our collaboration tomorrow.
Nice.
Okay. Oh, it's one of these guys. You're not sitting. I have to push you.
Mine I'm feeling a lot of pressure for. So next week I'm going out to Uppsala University to serve as an opponent on a thesis. I don't know if you've ever had to do this, but they bring in external people.
I haven't had to, but I've heard of it.
Yeah, and so I have to. Well, they invite me to give just a research talk the day before the defense, but in the defense I have to give like this 10 to 15 minute introduction. And like, it's one thing if I suck at my presentation, but if you like fail at introducing someone else, it feels real bad.
Yeah.
So I'm feeling that pressure right now. Like, I'm going to give a good intro. So that's what I spent all day doing today. So hopefully it turns out okay. All right. Maximinimus wants to know, is most of the HGCAL data actually meaningful or just stochastic features and of the showers? So what is HGCAL? What is its data?
HGCAL is the high granularity calorimeter, and it's this device I was talking about that will sort of image in very high detail, more than we've had in the past, what a quark, for example, being created, immediately forming a spray of hadrons, kind of collimated in one direction, and all of those hadrons interacting with, stainless steel, basically, kind of like Minos. Stainless steel will look like as it travels through a distance that is significant, that is, 2 meters, 2 or 3 meters. So the question is it mostly just kind of random noise? Is it actually meaningful or stochastic features of so the shower would be what this kind of spray of particles is in one direction. Yeah.
Put a percent on it.
Yeah.
What fraction of the data is useful?
So, I mean, in terms of estimating things like the energy, it's like all needed, right? We want to essentially count it up. We can't even for some kinds of showers, like quark showers, we can't even in principle count it all up because some of it is lost to, overcoming the binding energy of some nucleus. Some of it is lost in neutrinos, in certain decays and stuff. But we do want to count it all up as best we can to estimate better the energy of the shower. But you're right, in terms of understanding the features or understanding the underlying theory of quantum chromodynamics, the theory of the strong force that predicts how quarks are produced, unclear if it will be more useful than a kind of older kind of calorimeter that instead of having so many channels with so little energy and so much stochastic noise in them has bigger channels that can better add it up and kind of average out over that stochastic noise. Where this kind of calorimeter will be interesting is like 2 showers closely overlapping, which just look like one in an old, a lower resolution calorimeter. You might see that structure in this calorimeter. Or is there a new kind of particle, like a dark jet, something that, yeah, exactly, like some kind of weird new particle that doesn't behave quite like a standard QCD quark, but maybe travels some distance and then showers. You could see a lot more of those kind of features in this kind of calorimeter, to say nothing of other kinds of even less complicated particles that decay late or, you have something moving very fast that decays to a pair of things that normally would be so overlapping they would look like one thing in the current detector would look like 2. You could resolve it.
All right, Rachel, what is the answer? The top quark is as heavy as 340 electrons or 340,000 electrons?
It is 340,000.
Everyone guessed 340,000.
Great.
So
they knew the top quark was heavy.
Huh.
Yeah. So why is it so heavy? Why?
Non-dairy neutrino, the top quark is heavier than the electron? Huh. Today I learned. That's awesome.
The top quark is the heaviest.
I was going to say, what's the scale of quarks?
Elementary, exactly. The top quark is Well, it's like 175. It's as heavy as 175 protons.
Oh, wow.
And a proton is made of 3 quarks. Three up, it's up, and down. So one of the big questions that not just the LHC or any past or future high energy collider is trying to answer is, why is there such a hierarchy of masses among the elementary particles? And it really is a large hierarchy. You have the top quark at 175 protons. The bottom quark, the next heaviest, is about 5. The one after that, the charm quark, is maybe like, let me get this wrong, but it's like 2 or something. All the way down to the up and down quarks, whose masses have not been, really well measured, but are something like, a few MeV, down to the electron, which is half an MeV. So why is there such a big hierarchy?
I was going to say, wouldn't physics be easier if they were just all the same size?
Right, exactly. So many things. When you write down the simple models, like, again, Occam's razor, you try to put in the simplest ideas and think, well, if there is some large difference observed, there must be some dynamical explanation. It's not just like, oh, nature made it that way.
Yeah.
So this is one of the things we're trying to understand. And so we know that, the Higgs couples to these particles, and that's why they have the masses they do. Why is the Higgs, is there some reason the Higgs coupling is so strong to the top quarks and so weak to others?
So congratulations to those of you that said the top quark is as heavy as 340,000 electrons. You got a payout of exactly 1-to-1. So you didn't gain money, you didn't lose money, but you did get the confidence boost of knowing you had the right answer. So congratulations to all of you that guessed or knew that it was 340,000 electrons.
And I will not beat this.
That's fun. We should, next time you're on, we should do a what's heavier, the top quark, or like just pick another one. Like pair them off and see what, I'd be curious how people decide that.
Now I'm getting to the button mashing stage.
On top of that, why does a neutrino have mass at all?
Right.
Good question.
People are really interested in neutrinos. I found this as well when I taught particle physics, that students were very, very interested in, I have to wake him up, coffee. Does he need coffee? Is that the answer?
Where's Maximinimus when we need you? Non-dairy neutrino. Ironically, I don't actually care about neutrinos at all. That's awesome. It's a clever name.
Yeah, it's a good word. It like rolls off the tongue nicely.
Yeah. It's the sexiest of the particles in terms of verbal delivery.
Why do they have mass? I don't know that we know why they have mass. It's another thing that we search for a sort of dynamical explanation for. There's this idea of a kind of a seesaw mechanism where there's actually a really heavy neutrino out there, and there's some relationship between a high energy scale of new physics that causes one very light particle that we observe here, and then one very, very heavy one that would be hard to observe. It wasn't expected. The standard model works out just fine if neutrinos don't have mass, but it just turns out that they do. And we don't know much about their mass. In fact, I guess technically one of them could be massless. We know about the mass differences between the different flavors. So we only know about their mass because of flavor oscillations. The fact that the flavors can turn into each other implies that at least there are mass differences between the pairs of them. Okay, I'm
last guy. Anyone? Do you know
the last guy? I'm gonna look for coffee. That's my guess. He looks tired. If he's tired, if he's like me,
it's a coffee cup.
Yeah. Oh yeah. Here we go.
See, the key is not to give him to drink; it's to splash it in his face.
Oh, let's see.
I don't know. I just made that up.
Coffee. Come on, man.
I love that. And he's just gonna wake up and be.
Here you go. No, take it.
Drink it.
Okay, now
fool.
follow me. Didn't work. Come on. Can I bash it over your head?
But it's little things like that That's annoying. Gotta find a Red Bull for him. All right, Maximinimus, we need your help on this one. In the meantime, we should do another prediction because we're falling behind. Which one do you want to do?
How about
This one right here.
Yep.
All right. So we're going to talk about the W mass. Do you want to give a brief intro into what that is for those that are
sure
not in the know?
So, one of the underpinnings of the standard model of particle physics that we have been trying to test and kind of poke around the edges at is this electroweak unification, that the electromagnetic force that is responsible for light, electromagnetism, all kinds of phenomena we're familiar with, where the photon is the carrier of the force and it interacts between things that have electric charge. If you go to high enough energies, if you probe at high enough energies, and I don't mean high energy like, like you go to the gym and you work out and you're like sweating and that's high energy, like, particle collider energies, the kind of energies that existed just after the Big Bang, in fact, that at those energies, it is actually no different and is intimately related to the weak force. I think I'm going to just give up right now. I don't think I can get him. He's stuck.
Oh, nope. Minimus is back. Turn the lights on so he can see his way out. Oh my God.
What? Oh. I didn't realize I was in the dark. So that the weak force and the electromagnetic force are intimately related. And one of the key predictions of this is that there should be particles like the photon, but that are much heavier. The one that's just like the photon is called the Z boson. It really is just a photon, but heavy. And it also talks to neutrinos, which don't have charge. The other one that's like a photon but heavy is the W boson, and the difference is that it has electric charge as well. So it is charged. It talks to neutrinos. I mean, it interacts with neutrinos as well as with regular charged leptons that the photon also interacts with. The predictions, the predictions of the electroweak theory.
Isn't that an outlet?
That's an outlet, but where is the light? What is the thing I'm plugging into it?
Isn't it?
Can it? Oh, could it be this one? Yeah, maybe. That the predictions for the actual mass of the of the W particle, that's the difference. When they can, come on, man, come on.
Maybe open the door if he can see his way out.
Yeah. Okay.
What?
You gonna come?
No, we got closer. You can see his way out.
Come on. I wish I could kick him. I don't know how. Okay.
Right.
So
Sorry.
the mass of these particles was predicted roughly based on measurements, early measurements in the 1970s of the interactions of leptons, which are like electrons but heavier, so charged particles that are heavier than the electron, and interact both electromagnetically and weakly. The masses of the W and Z are precise predictions of the standard model, and very, very precise predictions. So we know so much about the interactions that we can predict the mass, not just to the second digit, but the third, the fourth, the fifth, really, really, really precisely. And so a very precision test of the standard model would be a very high precision measurement of the W particle's mass, which a couple of different collider experiments over the decades have attempted. Famously, the collider detector at Fermilab experiment did a reanalysis of their data and published a very exciting measurement of the W mass Should I keep talking? Because I don't want to ruin the thing.
Well, yeah, no, I haven't started it yet.
Okay. Very high precision measurement that was way off from the standard model prediction. And recently, CMS has come out with its own measurement, and maybe we can lead into the the question or the prediction.
All right, I will pop the prediction up right now. Oh, Old Man Fellini said, now try the coffee. I think that's a guess based on the cat shrug. All right, what have we measured with this, what is measured with the same precision as the W mass? Is it the Earth's mass or the human mass from a home bathroom scale? And so we're talking about accuracy of measurements or error bars of measurements. What has a similar accuracy as the precision we've measured the W mass with? It's the Earth mass or human mass from a home scale. I love the extremity of your questions. We don't get a lot of those, like, order of magnitude difference, but it's fun.
Okay. He's moving.
Oh, wow. Okay.
I got him to move.
Is there stuff in the way? I just hit him. That's key. All right. Measured with the same precision as the W mass, the Earth's mass, or human mass from a home scale. Put your answers in there now. Bet depending on your degree of confidence, one way or the other. We'll see how accurate that is. I can look up. Maximus said, open the door. Maximinimus.
Open the door. I gotta get him on the thingy, but...
What thingy?
Like, if I can catapult him out there. But I gotta get him...
Slingshot. We learned about the slingshot today, ladies and gentlemen.
Oh no, now I'm stuck. I'm stuck in the...
All right, you guys have about 30 seconds. Put your predictions in there now. Even if you're not confident, you might as well do it for fun. You can give someone else 10 internet points, or they'll win it off you. Either way, these points are useless outside of this channel, but it is a lot of pride involved in answering these questions correctly. So we measured the same precision as the W mass. Is it an Earth mass or human mass? Human mass from home scale. Should I check out the speed run? That might be a good... What level are we on?
We are on, like, level 1. Yeah, we're on accounting.
Accounting.
Or 103. We're on 103, sorry.
103.
Oh my gosh. Come on. Get out of the way. Go.
I might start a video. You guys might hear a voice on this. 57 seconds is the record on this one.
I'm at...
All right.
That would be a good order of magnitude.
Before I do it, let's do a prediction. Ooh, this one's close. 53 to 40%. 47%. Rachel, what is the answer?
The answer is the Earth's mass.
The Earth's
is measured
mass.
to the same precision, at least as of a few years ago. You know, the most recent data I found for astronomical, constants. Not constants, but astronomical measurements. The Earth's mass and the W mass have now been measured to 0.01% precision.
Wow.
And a bathroom scale, I mean, you probably could get a really good one, but is more than sort of like 10 to 100 times worse than that.
That's amazing.
So that was sort of a real exciting measurement when CDF came out with their measurement of the W mass that was 7 standard deviations away from the standard model prediction. This was a few years ago. It really excited people because it was one of the most interesting signs, potential hints of cracks in the standard model, maybe new physical laws that we'd seen in a while. And CMS recently... Atlas has made the measurement too, but CMS has recently done it to...
Oh no, you got to put him in a chair.
No, I think I can just push him out now.
Maybe the speed run puts him in a chair.
Oh, here we go. Put that down.
I choose bullying.
Just push. Go, go, go. Come on, man. Go.
I love that he's not pushing with his hands. He's pushing with like torso, just full body contact in this office area. Somebody call HR.
CMS's recent measurement is not quite as precise as CDF's, but it's maybe the second best precision that it's ever been measured with. It measures a number, I mean, it's something like, it's measured a mass of 80-ish giga electron volts to a precision of 9 mega electron volts, or close to that, maybe 10 mega electron volts. It's very, very precise. And it is, unfortunately, for physics beyond the standard model, totally in line with the standard model prediction. You can do it. Where are you going? Oh, yeah, get in the chair. Oh, I'm so bad at this.
No, you got this.
So bad at
One
this.
more, we're going to beat it. You've never beat this level before, right?
No, I don't think I've made it this far.
I think you can
I'm a
grab it.
parent. I could never sit for this long.
Oh, no,
No,
that's why Ask a Scientist Gaming is perfect.
Back in the chair, you...
Gives you an opportunity to play.
Oh, God.
Mediocre gameplay, expert science. Welcome all joining us.
And when I try to play the game, you know, then the science gets a little mediocre too. The explanations are a little bit. Come on, man, get in the
Old
chair.
man Felonius,
Get
the
in the
worst phrase in full accordance with the standard model. Man, I love
I'm gonna push you.
So I was on one of Ted's students' prospectus talks, and I learned about what is it, the theta, the like fraction of wrongness of the standard model. Is that what it is? Is it theta? I don't remember.
Fraction of wrongness. Come on.
Oh, we did it! We did it, ladies and gentlemen! Holy cow! We did it. Got a B with the damage, though.
D for
It's a
the
C.
time.
C is passing, ladies
Hey.
and gentlemen. Congratulations,
C is
Rachel.
passing.
You
C,
did it.
I would keep my Bright Future scholarship.
Good enough for Bright Futures. Good enough for Ask a Scientist Gaming. Lori, nice. That's what winning looks like. Still better than Alabama. Oh,
Right. It
man.
doesn't matter how much you won by.
Yeah, exactly.
Just as long as you
win any given Sunday. All right. So let's transition. Maybe we do Mario Kart. if
Yeah,
you're gonna play, 'cause we're
something
on the Switch
really-
already. Yeah.
Go back to something. So now the part how do I get out of here?
And you
Oh,
guys,
this time I figured it
you
out.
guys should all try talking about high energy particle physics while playing. Good job.
Or
and see
any-
how it goes.
Anything you think you know well,
Give it a try.
talk about, you know.
I mean, but it's a weird thing. Like a lot of people want to play like casual, slow games, but sometimes those are harder, right? Because it's easy to get distracted.
Yep.
I'll be curious how Mario Kart goes, because like you can't look away.
I like these games with one button. That at least takes a lot of other.
Yeah, that's fair. I think this one requires 2. So, all right, we're going to switch over. Ladies and gentlemen, we're going to play Mario Kart 8 for the Switch. The lowest scoring med student that graduates is still called doctor. Absolutely. Same with graduate students.
That's right. That's right.
C's get degrees.
right.
Hardest part about med school is getting in. Any particular reason you picked Toad?
Yes, because my daughter likes this
Oh,
character.
awesome.
Makes me think of her. And in this part, yeah, I don't really care about
Yeah.
particulars.
Stylize the
I'll
bike.
do,
All right, catching up on a few questions. Congratulations again, anyone that got that question right. You got a 2-to-1 payout. Totally worth it. All right, Leo Oz Fermi wants to know, what is the LHC looking for now? I mean, you guys found the Higgs boson. It's done, right?
Great question and a good lead in from this question of the W mass. So at the moment, I would say a lot of the focus is on precision measurements of standard model quantities. We are no longer, just make sure I have, okay. We are no longer doubling the amount of data every month or week or whatever, you know, unit you want to think in, like we were in when I started as a graduate student. And yeah, probably as a graduate student was the biggest time for that. Yeah, let me think about it. So when I was a student, my now husband, but at the time boyfriend, who also worked on the same thing, I think he graduated 1 year before I did and wrote his thesis on 1,000th-ish the data that I did, like 1 year later.
1 year later.
Yeah, it was
Reorder
something to that. Yeah, it was really, maybe I'm getting it, but it was like a much, much, much tinier amount. Maybe not 1/1000th. It was it he had
And
So
still
many
even
picobarns, and I had 5 femtobarns. Yeah, so maybe 1/100th or one, you know. So we're not in that regime anymore. We're in the regime where we're collecting data at a fast clip. So the accelerator is performing better than it ever has in terms of production of, you know, interactions per unit time, per unit energy, but is not doing that, can't really do them any faster, and we can't, you know, detect them any better or detect them any faster. So we are doing very detailed looks. We are trying to stop and think about collecting data in ways we hadn't done before. So like by optimizing, for example, for, I don't know, collecting W decays or Z decays, we didn't allow ourselves to also collect B meson decays, you know. And so what have we missed? What are some interesting ideas we might have missed by doing that? So we're trying to design these are called triggers, sort of sets of reconstruction criteria for collecting data that allow us to pick up on things we might have missed in the past. So some of the precision measurements are of the Higgs boson, especially the Higgs, and how it interacts with all the standard model particles. Because if we can the better we understand them, the more precisely we can measure them, and just like this W mass measurement, the more precisely the more sure we can be if we're seeing a deviation from the prediction. Because the predictions have also come a long way to be incredibly precise, and sort of the experimental precision and the theoretical precision in some cases are really driving each other, going neck and neck. In terms of searches for new phenomena, there's always been a lot of interest in so-called long-lived particles. The LHC, and again, it's like getting around the lamplight issue. The detectors are designed to detect particles that are produced and instantly decay at the interaction point. But there's no reason that new physical phenomena should be so short-lived. There's plenty of reasons, plenty of so-called natural reasons why something should travel centimeters, meters, and then decay. And it's hard to see because the detector isn't optimized for it. So people have gone back and tried to design algorithms to find things like that. And then there are these searches that are sort of, you know, we've always had this idea, like, what if we just don't know and we want to be totally model unspecific? And this has a new framing in the sort of AI language of anomaly detection. Like, let's try to be as agnostic as possible about what could be causing new physics and just try to look in a ML kind of assisted way for deviations from what we expect. So I'd say those are the three big things. And I said Higgs couplings, but there's also top quark interactions. There was a big measurement that got some press recently about looking for toponium. So it's long been understood that like the top quark is so heavy, as we talked about, that it can't form bound states like hadrons that live for some time that you could detect. But there's kind of if you look in top and anti-top production, there's this little feature that kind of suggests a very short-lived bound state of top quarks called toponium. That like this would have been the first time it's produced. So I think both CMS and Atlas have measurements of this.
Toponium.
Yeah, so it's not like new. It's not something that isn't exactly predicted by the standard model. Just something that is like a curiosity that would be hard to see in most cases. But we have the precision now to see it. So still talking about physics while even playing something as simple as this is not easy.
It's not simple.
I guess
There's a lot to digest.
I guess I am in first, so maybe it's not so bad.
Toponium. That's what I love about physics. Either it's a really like elegant and exaggerated name, or it's just a stupidly transparent name.
Right.
Toponium. I love it. All right. Let me follow up on some questions here. Why, Zach? Thank you for the follow. Thank you for joining us. Ask Scientist Gaming Mediocre Gameplay. Everyone that's just joining us, our guest today is Dr. Rachel Yohay, who's an expert at high energy particle physics, in particular what's going on at the Large Hadron Collider CMS detector. So yeah, if you have any questions, pop those in chat. Thank you for joining us. Thank you for join us in chat. If you have comments, you have questions, we would love to see them. We are talking high energy particle physics while playing Mario Kart 8. Which is a sentence not a whole lot of people get to utter in their lifetime, but I do every other week, which is pretty fun. Not necessarily particle physics, but whatever it may be. All right.
Now I get to utter it 2 times.
Yeah, exactly. But it'll be on YouTube forever, so anyone can enjoy this in the future, which is always a good time. Your kids will give you a hard time. Are they watching live, or are they going to...
I think they are, well, let's see. By now, they better be asleep. Yeah.
Ted's just like free for all night.
I think they were allowed to watch a little bit of it in the beginning. I wonder if they posted any questions. Oh, a kitty. There's a kitty here.
Interesting. The door was left open. I hope you're not allergic to cats.
I am not allergic.
Old Man Felonious said, I almost got to work on Methuselah, but I was deep in other work at the time and didn't have time, but it's a cool project.
Yep.
That's pretty fun.
So Methuselah, I was talking about these particles that live for some time as a bound state before they decay, or not even a bound state if they're elementary particles. And Methuselah is a detector that is designed specifically to find things like that. So kind of cool idea.
That's pretty fun. All right. Non-dairy Neutrino wants to know, do predictions for experiments at LHC require including gravity? Or is the Earth not massive enough? And surely the gravitational interaction between the particles is astronomically negligible, right?
Astronomically negligible is my new favorite phrase. Love it, non-dairy neutrino. I think you nailed it. It is astronomically negligible.
I mean, but this is something that's always bothered me because it's not zero, right? And so
it's not
like, like in quantum mechanics, right? We do DFT calculations and we can calculate a single electron exactly, but none of it includes gravity. None of quantum mechanics includes, because we don't have, a unified theory. But like when you talk about Schrodinger's cat, right? By quantum mechanics, it's a 50-50 chance of something happening. But doesn't it matter where you're standing in the room based on that slight deviation due to gravity alone?
Right.
Or is it so negligible it doesn't matter?
Well, if there really is, a theory of quantum gravity, I guess even the gravitational interaction would have like a Schrodinger-esque aspect to it.
Interesting.
But it really is negligible because the gravitational attraction between things of that tiny mass is nothing compared to, in SI units. So I'm thinking about this now, right? K, the electromagnetic, I don't even know what the name of it is because we always talk about the permittivity, but the thing K that's 10 to the 9 newtons per coulomb, like whatever the units have to be to make the math work out, is in the order of 10 to the 9, and G, like the gravitational constant is like 10 to the minus 11 or something. I mean, gravity only matters for large agglomerations of mass. And as I tell the students in mechanics, like we are very massive and we're relatively massive. We're made of like many, Avogadro's number of atoms. And we're standing on something like even way more massive. So we talk about like the normal force, like why don't you fall through the floor? Your weight exerts a force on the floor. The floor exerts a force back on you. Then I always say, like, why does it exert a force back on you? Like, that's because of electromagnetism and quantum mechanics, right? That's because of what's holding, the material, what makes the material up, all the stuff about, right?
Yeah.
So
the classic joke is gravity doesn't kill you on a fall, it's the electrostatics that do.
Right. Yeah, it's a complete completely different scale. And it only matters at high masses, high agglomerations of mass, and it allows things to form high agglomerations of mass because it is attractive, always attractive.
Maximinimus, in principle, could you measure G by seeing the particles fall down through the detector? I don't think you're that accurate. Theoretically.
In principle, right, like if you could measure the curvature, the deflection of a particle's path due to gravity.
Oh man. So follow-up question. Unlimited budget, no moral qualms. What experiment would you do? And the answer is put a particle accelerator next to a massive black hole and see how much it matters.
Right.
Like that's what it would take, right?
Yeah, you would need a very large gravitational interaction, and still then you're talking about quantum. I mean, we kind of know what happens to photons near massive objects, right? They do respond actually to the curvature of space-time. They bend, right? And so that's how gravitational lensing works, and why you see those rings around, galaxies that have some heavier clump of dark matter in front of them. So I guess that's one way of measuring G, is to look at lensing
of these particles.
If you have a known mass or a known whatever curvature due to a black hole or something, and then look at what happens to light as it tries to reach you.
All right. How is Mario Kart going? You're feeling better about this?
Better,
or worse?
yeah. It's definitely going better.
And you guys will have to let me know on the volume. We're switching games, and always it's a crapshoot whether the volume is correct or not. But you guys let me know. But yeah, we just crossed 9:30. Ask a Scientist Gaming, mediocre gameplay, expert science. Dr. Rachel Yohay is playing a little bit of Mario Kart while talking about high energy particle physics, talking a lot about neutrinos, whether she wants to or not. But if you guys have questions, we are happy to answer them.
If your audience would like to know about neutrinos offline, I will recommend some possible game players for you. Yeah.
That is my follow-up email every
I can't promise they'll say yes, but I definitely
My success rate is about 25%.
Really?
From suggestions from guests. It's about 25, which isn't bad. I mean, considering this ask is a bit weird. I mean, even for you, not a game player, I appreciate you coming on, because
I think a lot of people probably they're nervous. Like, I don't want to put myself out there, and I don't play games very well. But,
the audience will judge you accordingly. Your H-index be damned. You suck at Mario. It's going to cost you.
Right.
All right. Leo Oz Fermi, following up on the discussion we had, detectors tend to have a magnetic field to distinguish positively and negatively charged particles, and that far outweighs the gravitational effects. Yeah, I mean, that's electrostatics is very, very strong.
Right.
Shmonite, wait, we're a bit weird? Is that what you said? Yeah. Anyone that shows up to talk science while playing video games, we're a collective group of weirdos, and I love it. Thank you all for joining us. We really appreciate it. All right, Leo Oz wants to know, any news from the A-Trap? First, what is the A-Trap, and what is the news from the A-Trap?
A-Trap, I think, again, not totally an area of expertise, but it is an experiment that tries to create anti-hydrogen and trap it, and hold it there for some time. And I think these trapping times are significant, like seconds or milliseconds. I can't, long enough you can count or do experiments or put it in a magnetic field and see what happens. And so they're trying to create so what's hydrogen is a proton and electron, so I guess anti-hydrogen would be an antiproton and a positron.
Positron, yeah.
Yeah. Huh. And they're trying to look at the charge symmetry, parity symmetry, all the different symmetries between particles and antiparticles by trapping anti-hydrogen for some amount of time and doing experiments on it. And I don't know the latest on that experiment.
That's fun. But that is a great segue to this prediction right here. Matter-antimatter asymmetry.
Oh, yeah.
Oh, let's do it. All right, we're going to put up a prediction right now. If you're not following us, click the follow button. because we need to know the answer to this question, and you guys are going to tell us that answer. Actually, no, Rachel's going to tell you whether you're right, but you guys are allowed to predict things based on your standard internet units and confidence in the question. But okay, so matter, antimatter, asymmetry, probability. Can you frame that within the context of this question before I post it?
There is a tiny asymmetry. So since you guys are all scientists, you're all nerds, you know that when matter touches antimatter, they annihilate into, photons, or into pure energy. And so why is there anything in the universe, especially early on in the universe when it was hotter and denser and things interacted much more frequently than they do now? Why didn't all the matter find all the antimatter and annihilate into energy, and we wouldn't be here having this conversation? Because there is a very, very, very slight preponderance, sort of primordial, I guess, preponderance of matter over antimatter in the universe, and it's essentially responsible for all of the matter that there is. So what is the size of that asymmetry? I guess that's what's meant, that's what we mean by asymmetry probability.
Yeah, so like, is it 1 to 10, 1 to 1,000?
Right.
And we're going to give you comparative metrics to do this prediction, which are pretty spectacular. So the question is up right now, matter, antimatter, symmetry, probability. So this is basically the ratio. And so is it the same as being struck by lightning, like whatever those odds are, 1 in a million, or perfect March Madness prediction bracket? Very contrasting things. So what are your odds of being struck by lightning? What are your odds of getting a perfect March Madness predicted bracket? And how does that relate to matter, antimatter, asymmetry, probability? Is this a known question, or you just came up with this one?
This one? You mean...
Like in terms of...
We know the answer. I mean, we know what it's not something, we know what the preponderance of matter over antimatter is. Yeah.
And so you're like, what is as
likely? Yeah.
So you just looked up some random stats and
yep.
Wow, that's fun. I look forward to discussing these.
Am I crazy? Shouldn't I be able to find... I can't be Bowser. Can I be Bowser?
Yeah. Bowser.
Where is he? Right there. Thank you. So this is for my son. He's asleep. But...
Shout out to your son.
Yeah.
We're playing as Bowser. You guys have about a minute left on this question. What are the odds, matter, antimatter, asymmetry, probability? Is it similar to being struck by the odds of being struck by lightning, or predicting a perfect March Madness basketball bracket? Non-dairy neutrino. We'll follow up on this one afterwards. What if all the antimatter is just over there? Occam's razor, we're going to call that the correct answer. That's amazing. There are several theories, but none of them are that good. That's interesting. Old Man Felonius, I remember they were measuring the gravitational effects on anti-atoms and found no difference from matter. There were some hypotheses that this put an end to. Poor theorists. Oh, interesting. Like, was there an anti-gravity equivalent for antimatter? And the answer is no, gravity was universal, which means it's not charged. Interesting. All right, Rachel, what is the answer?
It's always attractive.
Matter, antimatter, asymmetry, probability. What is it, Rachel? The equivalent of being struck by lightning or perfect March Madness prediction?
Right, it's like 1 in 10 billion. Yeah, 10 to the 11, which is more closer to getting the chance of getting a perfect bracket.
Wow.
It is much higher than the chance of being struck by lightning. Much smaller. You see what I mean?
Yeah.
Much less likely than the chance of being...
Here. So the odds of being struck by lightning is 1 in a million. The odds of predicting a perfect March, this is random guess, right? 1 in 10 billion. Yeah. 1 in 10 billion to 1 in 100 billion, depending on the prior knowledge. So yeah, it is much closer to a perfect March Madness bracket, which people were very confident in. 97% of betting went towards that one.
Yeah, it's a very small asymmetry of around 1 in 10 to the 11, 10 to the 10. But it's responsible for all of the matter in the universe.
Huh.
And yeah, understanding the source of it, exactly how it came about, that's also an interesting open question.
That is fun. So congratulations to you that knew the answer, were confident in that answer. Enjoy your standard internet units. You can unlock emotes, you can request a factoid, you can make us drink alcohol. Totally up to you, but more pride based on how you answered that question. So how do you feel about Bowser versus Toad in this?
I feel like more, I don't know, more angry or something. I feel, I don't know, I look bigger and then I must be going slower or something, but like, you know.
No, I think that there are different, at least in the Super Nintendo version, like Bowser had a higher top speed, but his acceleration was slower. It took him longer to get there. And Toad, I think, had more control. Yoshi was a balance, but somebody can correct me if that's not true in Mario Kart 8, because I have not looked up recently. But I know for the first one, all the world records were with, like, Bowser, because when you hit top speed, you were
This is one of those games people really do.
Oh, man.
Go.
Optimize the hell out of it.
Yeah.
Well, especially the new one, the Switch 2. There was, like, a record every 3 minutes or something. It was ridiculous.
I think you should be good at this game if you're, what's that, like, downhill slalom? You know, like in skiing, where they have to go, like, just close to the, you know, as close as they can possibly get to the, flags without, being on the wrong side of it.
And they're going like 50 miles an hour or something ridiculous. Yeah. Oh man. All right. Old man Felonius wants to know. Okay, actual question rather than a comment. Do you think that dark matter could be only gravitationally interactive, or are you pretty sure it can interact with standard model stuff? Do you think dark matter could be only gravitationally interactive?
I mean, this is the 30 years of searching and not finding can make one pessimistic that, yeah, it's just gravitationally interacting.
That's it.
The history of unification of forces, you know, and makes you maybe optimistic that, yeah, why would it not talk to the other forces? Why would it have some charge? Many of the particles we know about, the quarks, let's say, they feel the strong force, they feel the strong or quantum chromodynamic force, they feel the electromagnetic force. Why leptons feel the weak force as well as the electromagnetic force. It's not crazy to think that dark matter would feel something more than the gravitational force. Of course, they all the massive ones also feel the gravitational force. So it's, you know, I'm an experimentalist, not a theorist. You know, I don't. It feels weird to say what do you really think? You know, about something about which we have very, very scant experimental evidence.
Yeah.
So.
But it's fun.
Yeah.
If you were a betting person.
If I was a betting person,
yeah.
I guess I would bet that it is, it does have some feeble interaction.
Interesting.
And we just, you know, we just haven't seen it yet. Yeah. Or its interaction, yeah, because where am I now?
You're on the wall. So yeah.
This is.
Up that.
Oh, I see. I see.
You're on a wall.
This is Mario. This is the game telling me I'm wrong.
Exactly.
That there's no way.
But also, it lets
this
you know.
particle will be found.
The gods of Mario have spoken, ladies and gentlemen.
Yeah.
That's fun.
Sometimes things just have, you know, Democritus comes up with the idea of like an atom, but then it was how many hundreds of years until
2,000 years
or thousands of years,
Yeah.
until that really was a relevant concept, you know?
Yeah. But counterpoint, the number of people making shit up back then, one of them was going to be right?
Fair, right? And maybe we only remember the guy who was right.
The Nostradamus is right.
Right.
1 out of 100 times, therefore, yeah.
Right.
Because we just went over this, Plato was imagining, you know, so Gen Chem 2, I started with an introduction of, you know, atoms, Lewis dot structures, making structures, and they have polarity and whatnot. And I start with an introduction about Plato, and Plato thought there were 5 elements, right? Like earth, fire, ether, water, what I missed. But anyway, those were the five forces, and he actually attributed them to shapes, platonic solids. And so, like, fire was a tetrahedron, Earth was a cube.
Earth was a cube, okay.
It's built with Earth. And so, like, he just kind of made that up. And turns out he's not that wrong, right? Like, these tetrahedron, octahedron, those are the shapes of molecules.
Ah,
And
yeah.
so he was right,
Okay.
but for the wrong reasons. But he also had this thought of, you know, if the Earth is governed, or the universe is governed by rules, those rules probably follow mathematics. So something as simple as platonic solids makes sense.
It's kind of amazing how far many, you know, early, let me say early, but, you know, scientists throughout, before, let's say, the Industrial Revolution, got on just geometry.
Yeah.
Just like thinking about what, yeah, like you said, what shapes seem symmetrical or have
Yeah.
special properties. And like, I think it was Kepler, you know, calculated a lot of the basic features of gravity without ever really having to make reference to a force.
Yeah.
Just because, like, it, you know, it's a central force, and so you get all these orbits, and he knew, you know, he knew how to calculate all that stuff and was totally right, and just didn't have the explanatory picture.
And a lot of it's just like simple symmetry and elegance of the math,
Yep.
and it just
Yep.
like works out. It just
And we're
works
still
well.
we're still exploiting, you know, symmetry arguments and how we come up, because they have been so successful. I guess they're kind of related to Occam's razor in coming up with theories in particle physics. So, you know, electroweak symmetry, the idea that these two forces are related, and, you know, the symmetry groups guide a lot of the development of the Standard Model, and so of course people think they will also guide development of physics beyond the Standard Model. That it like, there's some, I can't remember who said it, but like, nature should be, you know, as simple as possible, but no more simple, or something, you know?
It's a good description of evolution, right? Like,
Yeah.
it's just energetic optimization.
Yeah.
right? Simplicity and elegance in the answers. I like it. So yeah, if you guys have questions for Rachel, go ahead and put those in chat, but I'm going to ask one of our canned questions I like, and I honestly don't remember your answer last time. I apologize. It's been 4 years and 100 and something guests since then. But the question I like
Hopefully
to
I
ask
remember the
everyone,
answer. Or no.
what movie or TV show gets your discipline right and what gets it wrong? In terms of either how they talk about physics, how they represent physicists, how they represent Large Hadron Collider, movie or TV show?
Well,
And has anything
okay.
come out in the last 4 years that would change your opinion?
I haven't watched that much of The Big Bang Theory. I've maybe seen an episode here or there, but I know, isn't the conceit that the guy has like 2 PhDs?
Something
Like, that's
that.
wrong.
Somebody in the audience knows this.
Yeah, it's hard enough to get 1 PhD.
Yeah.
And even if you get that 1 PhD, have it be like, you know, meaningful. And so the idea that you'd have 2, that is completely wrong.
Why would you even go back for a second one?
Right. Why? Yeah.
The one scenario where I'll see like double degrees, MD, PhD, that makes sense.
Yeah,
You
that
can
makes
experiment
sense.
on humans.
Right.
The other one is getting a PhD in sciences and then getting a PhD in education,
Sure.
because then you can do some really cool research on that front. But yeah, I don't know what his degrees are. If anyone in chat knows, feel free to throw those in there, because I don't know. Big Bang Theory has always rubbed me the wrong way. It's like, it's kind of nerd blackface, like
Yeah.
overrepresentation.
Yes.
Like,
Yes.
yeah, I get it, you're autistic, but also there's a pretty aggressive critique on the chauvinism involved. Like, he regularly belittles women.
Oh.
Maximinimus, if you had a link in there, I don't know if you had a filtered word. I don't know. Yeah, that filtered it on chat.
Oh.
But anyway, yeah, if you guys have comments on that, we would love to hear them.
What gets
anyway.
it right?
I know there's been a bunch of sci-fi books on, you know, particle accelerators and things like that. I read one where there was like a conflict between a cult that wanted to have the end of the world and scientists. Like, that's not uncommon, but I don't know about movies.
There's a great, like, documentary about, so maybe that's cheating a little bit,
Yeah.
about what it was like in sort of run 1 or the early days of the LHC experiments, called particle fever. And that felt very true. I mean, it helped that you kind of like some of the people in it you knew, and like, but just capturing the excitement of building, because you're waiting and waiting and waiting and like working to build this experiment for a long time before it can actually turn on. And there's all kinds of, there was a big accident with the LHC that delayed its real startup for a year. And that's after like a bunch of other delays that just had to do with the construction and like schedule overruns and stuff. And you're waiting, and like you've done all the optimization and you've done all this work, and you've like generating like fake data to kind of practice how you're going to reconstruct the real data. And then when it finally like turns on, and it's like, they capture that moment very, very well, I thought. Awesome. But it is a documentary, so it's a little bit of a cheat. Yeah. And the movie, I guess everyone's seen the movie Contact, kind of has the same vibe, right? It feels very true to life about what scientists are like and kind of what motivates them. And it's not about particle physics, but...
No, that's a good one. The ambiance of it really captures something. It's the genuine curiosity.
Yeah. But in terms of like explaining...
the thing that's best about Contact, spoilers, is that like... as far as everyone else is concerned, she experienced nothing because it was an instant, but for her it was like a thing.
Right.
That also happens, where you feel like it was the most important experience of your life and nobody else cares, and your paper does not get cited.
Your parents are like, when are you going to finish this thing?
Exactly. Contact is one of my favorite movies. Yeah, that is a really good one. It's been a long time. I need to rewatch Contact. That one's been a while.
I'm trying to think of a movie really about collider physics or about...
Yeah, you get a lot of astrophysics, right? You get space travel regularly.
I remember, I forget which one of these disaster movies from the maybe late 90s or early 2000s, there was something about like the neutrinos in the center of the Earth are like acting weird. I don't know. It was like, and then I don't know, the Earth was the core, maybe. I forget the name of the movie.
It was neutrinos. The core
totally...
is one where they had to turn on the core again.
No, maybe I forget. But they said something in the movie like the neutrinos are mutating, or I don't know. They used some other like nonsense science word. I remember seeing that and being like, oh God.
If anyone knows where that quote came from, please put it in chat, because I'm genuinely curious. It might have been something I blacked out. Misadventures. Tony Stark made a particle accelerator in his living room.
Right. And I was just thinking of there's is it Spider-Man Into the Spider-Verse, where they have like a big fight in a scene that looks like suspiciously like kind of the inside of the CMS detector. Like there's some kind of collider, and they're fighting on the collider.
That's fun.
And then they gotta prevent someone from going to another dimension. I should know this better. This is another one. My daughter's like obsessed with this movie now. I kind of forgot the plot. That probably did not do it justice.
Max Minimus wants to know, what did Dr. Yohay think of Oppenheimer? Have you seen Oppenheimer?
Yes, I have seen Oppenheimer. Oppenheimer...
it's Spider-Man Into the Spider-Verse. It was the cartoon one where they had, it was the collider to get to his multiverse where his wife lives.
Yes.
Yeah.
When I introduced myself, like the first day of class, sometimes I show a still from that movie, and I'm like, oh, this is like I say I work on the CMS experiment, and like here it is in like movies. Here's what it looks like in Hollywood.
That's awesome. Multiverse confirmed.
Thank you for reminding me of Oppenheimer. Of course. I hope it's not cheating. I mean, it is historical, obviously, and it's
with some embellishments.
History that is the development of the field that probably most directly relates to collider physics. If we have big science and experimental collider physics or experimental high energy physics in the world, but especially in that movie in the United States at all, it is a direct outgrowth of the Manhattan Project and sort of the cachet that all of those scientists gained from the successful deployment of the bomb and development and deployment of the bomb, that basically when they kind of went back into their labs in peacetime and were like, hey, give us a bunch of money so we can study these nuclei. Like, they're more interesting than just weapons. They got it. So that movie, especially the beginning, you know, there's a whole interesting part of the movie where they're talking a lot about the kind of political fallout of what is it in the end? About the development of the hydrogen bomb versus the fission weapon. And but the first part of the movie where they're just kind of studying quantum mechanics and really, really excited about it, and like doing small experiments and just discovering new things, that also felt that also kind of got the vibe right, and the way they show the labs. The idea that we are, you know, obviously the field is so much bigger than a couple of guys who are really excited, guys and gals who are really excited about, you know, the quantum theory they're studying on the continent or whatever, that they're going to get on a plane or get on a boat and, you know, go ride around Europe to find just the right professor to teach them. It's obviously very different now. We're a much bigger, more unified community, but it captured the excitement and the way people do science very well. I just...
All right, thank you to Old Man Felonius, who quoted, it is the movie 2012 is the one we were talking about.
Thank you.
Here's the quote. It looks like the neutrinos are coming from the sun, have mutated into a new kind of nuclear particle.
Yes.
They are heating up the Earth's core and suddenly act like microwaves.
I knew there was a connection to the Earth's core.
Holy crap. It was 2012 disaster movie. That is amazing.
Yes.
The neutrinos coming from the sun have mutated into a new kind of nuclear particle. Rachel, you're going to be very disappointed when this turns out to be correct. This is what's actually happening, and you guys are all getting it wrong. Mutated into a new kind of nuclear particle. Oh my god. Yes, exactly. I'll put the quote in chat so you guys can read it for yourselves, because I did not. Man, the seriousness with which he delivers this line is amazing. But there's the quote right there, ladies and gentlemen. All right, game-wise, what do you want to do?
I think I could switch to Pac-Man.
Pac-Man.
If that's not too much.
Pac-Man. Yes.
Here,
I will do the switch over, but I'll give you a question first. Non-dairy neutrino. Sorry I missed this. We're going to revisit it now. How much does simulation or other theoretical predictions guide which experiments are actually done? I'm a computational physicist, so I would hope the answer is a lot. Intuition versus experiment guided or theory guided?
So in terms of, I would say that many large particle physics experiments, or even small ones, are targeted at a, let's call it a broad class of theoretical models. So somebody on the chat brought up Methuselah, which is a great example. There are a lot of theoretical models that predict particles that all share the feature that they will decay some measurable significant distance from where they are produced, and therefore the detector should be kind of far away from that point, but also connected to the timing of the interactions that created the particle. So in that sense, the basic, just making sure I can get this closer. The basic parameters of the experiment, or broad outlines of it, are usually guided by a class of models, or take the general purpose experiments at the LHC, which are guided mainly to detect the Higgs boson should it have a mass anywhere over, 1 decade in mass, basically. Beyond that, then I think, experimental reality guides it more. We have a long, literature about how to detect charged particles, neutral particles, particles that interact electromagnetically, particles that interact hadronically, depending on their energy and their mass. We have a long, literature about how to do that and how to build detectors that will do that. That's going to apply no matter what the underlying theoretical model that one is searching for will be. And in terms of calibration, you also want to be able to, so sometimes called rediscover the standard model, remeasure the things that you already know are there and make sure that the detector is working right. Detector design, the very specific engineering of it relies heavily on simulation to understand exactly, to model this passage of particles through matter, to understand the effects of making the detector one size or another, making the channel count one thing or another. There's also a lot of work to simulate the noise of the electronics, and also how they will age with radiation. So I guess that sums it up.
All right. You ready for some Pac-Man?
I am.
All right. Just joystick on this one.
Okay.
We're playing on the arcade joystick. We're doing an arcade emulator. This is actually Mrs. Pac-Man and not Pac-Man.
All right.
Someone's a purist, but it is the same game plus a bow. Plus
love it.
Slightly different maps, but that's fine. Leo Oz wants to know, what do you think the next sensible objective is? Dark matter? Presumably objective in terms of understanding. Is that the next big breakthrough? What's the next Nobel Prize for particle physics?
The next Nobel Prize. Oh, that's a good question. Am I really that bad at this too?
Yeah, it's a little, the timing's a little jank because you have to turn earlier than you think.
Oh, okay, so it's not just me. Well, I guess the last ones have been kind of celebrating, you know, if the idea is to award it for something that's kind of already known, but maybe its importance wasn't appreciated. I guess we've had for neutrino oscillations. So maybe when we measure the neutrino hierarchy, mass hierarchy, that would be one of them. I'm really having trouble thinking for something completely new. I don't know, maybe there's a quantity in particle physics called flavor. So I was mentioning before that there are, now the people have to watch me.
No, it's fine, keep going. You're doing great.
Where there are basically three families, for example, of leptons. There's electrons we all know and love, and then there are just like heavier electrons. They're called muons and tau leptons, and like why they exist, why there are heavy ones, nobody knows. I think if we understand the family structure and why there are three families and no more, no less, maybe there are more that are very heavy and we don't know, that would absolutely be a Nobel Prize worthy discovery. But that's, if that were true. In terms of things, and maybe this is a little bit pessimistic on my part, I feel like a lot of the things that are Nobel Prize worthy to know, the Nobel Prizes have been awarded. Which is another way of saying that it's like been a while.
Yeah.
You know, the Higgs Nobel Prize was given out the 1 year after the Higgs was discovered. And I'm trying to think of one of the big open questions that we actually have some answer for. And I am struggling, I have to say.
I mean, so going back to dark matter, if that has some sort of charge or someone can definitively show that.
Yeah, that would also be a Nobel Prize. That would be a huge, huge discovery. And it would, if it is a particle that that does interact, that we detect through its weak or electromagnetic or whatever interactions, it would have some, if it has just weak, like the weak force interaction, I guess that would be, it would be cool to have found it, but it won't be any new thing to study. But if it has some new force, some new feeble interaction, then there will be a ton to study. And that would be, that would be like there are 4 forces that we know of: strong, weak, electromagnetic, and gravitational. And there would be, a fifth one, basically, a fifth kind of interaction. That would be something new.
And that's beyond Nobel. That's shaking all of physics, right? That's Newton-Einstein type event.
I don't know. Is the discovery of radioactivity a Newton-Einstein? I mean, it would be kind of in that vein. Event. I guess it's up to your
What you think?
What you think? Yeah, I guess
Changing, textbook changing.
Definitely textbook changing. Okay, what am I doing?
Is this the Pac-Man you remember of old?
This is oh yeah.
Oh, so close. Ouch.
You know what I'm gonna do?
Misadventures in Astro?
I'm gonna blame my equipment and move this
Yeah.
closer to my
Right hand, exactly. You need the glove. You need like a fingerless glove for proper video gaming. All right, Misadventures in Astro. Has anyone asked her about Sabine Hassenfeld yet? Apparently she missed the part of history of why we kept particle scientists employed after the war.
Oh, I know who she is. So she's a theoretical particle physicist who is very skeptical of the really of like big science. Like it's not that she doesn't think particle physics is worth studying. I mean, she studies it, but that these big collaborations are not, collider experiments are not really bearing. Did I get it?
It's a cost-benefit question.
Yeah, are not really bearing the fruit that they promise, and that the money, assuming there is some, you know, this is where I think one of her fallacies lies, that there is some, like, you know, imperial court that sits around deciding, you know, we have 10 million units and we shall spend all 10 million on the LHC, or 5 million on this and 5 million on that. It doesn't quite work that way, but that we are kind of chasing the same ideas in the same way, and that some new thinking is needed, and that maybe more smaller experiments would be a better use of the money. And so she's been kind of like critical of the sort of consensus support for Collider, for the LHC in particular, publicly, which doesn't often happen, because in our field, because we need a lot of money and we need a lot of human resources as well as financial resources to do what we do, we often kind of all agree. We even have a decadal planning process where we literally try to agree on what should be the priorities. So, you know, there's something to that. And in our recent decadal planning, a strong support came out for, you know, a dedicated stream of funding for small, agile experiments that could address, to the point of the person who asked about, do experiments
Nice.
use simulation, and what kind of questions do they address, that could address dedicated questions, but that would miss out on some of the bigger pictures. You know, these agile experiments are not going to be producing Higgs bosons. And a lot of support came out for that, and we'll see if such a dedicated funding line, you know, is created. How we actually fund things in the US, you have to convince politicians, right, to support them. And it's very important to remember that it's not like money is sitting there, and if it's just owned by particle physics or owned by physics. Which one do I press? Okay. Owned by physics, and that if it's not spent on one kind of physics, it'll get spent on another. Like, it might just disappear altogether.
Yeah, that's
like
a good
I
point.
suspect might be happening with our, you know, fiscal troubles in the United States. So there is also a price to pay to be too critical of, you know, you want to strike a balance. You don't want to like silence critics, because they're important. Like, maybe we are spending our resources poorly, but you also don't want to unnecessarily make it seem like there's less agreement or less scientific validity to collider physics than there is.
Yeah.
You know, just to
There's a
get
cost.
some views. I don't know.
That's a fair balance.
She's one person. I think the thing is, I don't know that scientists are so easily are quite so cynical. You know, like if collider physics, we have an idea of what we'll see at the HLLHC and what would be like a great add-on. You know, we think we will measure the Higgs couplings quite precisely, and if there's new physics, like even better. That still kind of makes it worth doing. And I think if things continue to go that way and we just get more of the standard model, I think even the scientists themselves, who are the first people who have to be convinced, will also come around to the viewpoint that new experimental methods are needed.
And that's what, like, there's this conspiracy that scientists are just like pushing evolution because we're anti-God or whatever it is, right? That's a certain perspective. And like, you're just going to accept anything that supports evolution. And I can assure you that most researchers in this area would love to find something that completely debunks evolution. That would be the most profound contribution to biology in the last 100 years.
The Nobel Prize,
exactly.
Right? The textbook defining.
We would love to have that. No one's suppressing it. If that happens, it will get published and it will be picked up. But like, we don't have that. There's a reason. Surprise. All right. Old Man Thelonious, before the LHC was turned on, were you involved with all the questions of micro black holes destroying the Earth? One of my favorites was a website that is still, has the Large Hadron Collider destroyed the world yet?
Right, and the answer is always no.
There you go. There's a link to it if you guys want to check it out. It's kind of a...
No, I was not involved in any of those kinds of calculations. I want to say that was like kind of in the news. There was this guy in Hawaii who tried to like sue to stop the turn on of the LHC. And I do remember that news story coming out when I was a grad student, but you know, I did not participate in that, the defense of the LHC.
It's fun.
But I'm still here. We did not create the black hole.
Contra, welcome back. Thank you for joining us. Greetings, docs. Hate that I'm late, but I'm glad there's a VOD. Absolutely check it out on Twitch or on the YouTube channel. YouTube channel apparently has better volume balance for whatever reason than the VOD does on Twitch. But anyway, a few guests ago I asked if dark matter could be black holes roaming around the universe, but now I'm thinking maybe there are highways of gravity that have developed as multitudes of aliens have used gravitational propulsion. Thanks for joining us, Dr. Yohay. Is it aliens with gravity? No. Highways. It's aliens using gravitational propulsion.
Highways of gravity.
So aliens have invented a gravity-driven vehicle, and that's what we're seeing as dark matter.
Multitudes.
That's not a real question. Do not take that too seriously.
Okay.
But I hope that's true. I genuinely hope that's true.
I don't think there are highways of gravity.
I think we'd see it if there were paths of gravity, right?
Yeah. Well, like, okay. If you look at these large-scale structure surveys of the universe, right, like where the galaxies are, like you see these like filaments and voids. There's like spots where there's like lines of galaxies and then there's nothing. So at that scale, you really do see structure. Like, is that a highway of gravity?
Interesting.
Yeah, I don't know.
Alien gravitational.
Now, what are the aliens? Yeah. So is there some there's already electromagnetism that created the chemistry of these aliens?
Yeah.
And then they gravitational propulsion.
Yeah. I love that sci-fi thinking. We'll take that. All right. Thanks for joining us, Dr. Yohay. When you run the LHC, does the data return actually look like the screen that you have to decipher? Or what does the data return actually look like on the screen that you have to decipher? So it's not what you see in the, I don't know, sci-fi depictions.
Yeah. That's a good question. So it depends at what level.
I'll start you again if you're ready. You want to take a break?
I'm going to take a break.
That one?
I feel like I've bungled so many like easy ones that I need a minute to.
No worries. Well, you answer that. I'll run to the restroom. So
awesome. Yeah.
What's the data look like?
So on while we're actually taking the data in real time, there are people in a control room monitoring the quality, and the data look like histograms. We view it as histograms of quantities that we want to measure. Heat maps, because the detector has many channels, and so we can sort of unroll the detector into a 2D projection and make a heat map of, say, which channels are being hit more. Maybe we expect it to be uniform, maybe we expect it to be more hotter in some spots and weaker, colder in other spots. If we see a really, really hot spot, we might conclude that there's a channel that's broken or misfiring, something like that. So in real time, it looks like histograms and heat maps. But of course, it's bits, it's all ones and zeros. So some significant processing is already happening there. We do also make what's called event displays, which are kind of a throwback to the old days when the data were photographs. Yeah, humans cannot see it all in real time. We have to make histograms, basically, computational. We have to feed it through a computational algorithm, even to monitor it in real time and sample just a little bit of it. So event displays are throwbacks to the old days when data were photographs. Something would happen in a bubble chamber. The bubble chamber has a window, literally a glass window, or a plastic window. There's a camera, and the camera fires. And people would look at pictures of the tracks going through, the bubbles basically going through. That's not how we take our data anymore, but as people are used to thinking about the interactions happening that way. And so we create a computational image of what an event or a subsample of events. As Liaz Fermi points out, you can't see it all in real time because it's happening at, I think the readout rate at CMS is tens of kilohertz, right? So you obviously can't look at everything at once. But some of the events will get sampled to make these sort of computational event displays. And you have kind of a picture of what the detector looks like, and a muon went here, an electron went there.
Dairy has a good descriptor of that. Is that the picture with the shooty outlines?
That exactly. The picture with the shooty outlines, exactly. Then once that's the sort of first level, then the data gets processed again and sort of treated with the best, most up-to-date calibration and alignment constants and everything. And when you, grad student, then go to analyze some new data to write your thesis, then it looks, it doesn't sort of look like anything. You picture every event that happens has, lists of particles that have lists of momenta and mass associated to them. And you start doing kind of relativistic kinematic calculations to calculate whatever it is that you want. And then it's very computational. It looks more like, I guess, a computer science. You would interact with it more like a computer scientist would, until you finally make a histogram or a heat map, usually a histogram of something that you're interested in.
That's fair. All right.
Okay.
Go. You got a break.
Ready.
All right, we should drop another prediction. We have some time. Which one do you want to do? I kind of want to do this one just because this is...
Oh, yeah. Okay.
That's just a fun one. We'll get back to particle accelerators. We're going to pop up a prediction right now. While I was out, Average McDonald's Cedar, which is an amazing name. Thank you for the follow. Thank you for joining us. You are the 960th follower, so thank you for joining us. If you have a question, throw it in chat. We'll be happy to answer it. But right now, we're going to pop up a question for you guys, which is kind of fun. So I'm going to put this up here. You guys are going to have 2 minutes to answer. Use your standard internet units. If you're not following us, click the follow button. Second, I gotta... All right, I'm going to pop this question up right now. If you're not following us, click the follow button, get your standard internet units. You can use them to pick one of these answers based on a question that Rachel is asking you. So, Large Hadron Collider, it has superconducting magnets which need to operate at low temperatures, but it's not always operating, and so sometimes it gets warmed up and then it gets cooled down. And so this question is, when you cool it down, it's going to shrink. what is the amount of that the LHC shrinking? And so there's its 27-kilometer ring, and so the question is, when you cool it down, I guess it's liquid helium at the core, right, for the superconductors. So that's 4 Kelvin. And then outside of that is 77 Kelvin, which is liquid nitrogen. And so the question is, how much does that 27-kilometer ring shrink when you cool it down? Is it 8 centimeters or 80 meters? And for reference, 8 centimeters is the length of a finger, and 80 meters is the length of roughly a football field. And so, yeah, how much does it shrink when you cool it down? Is it a little or is it a lot? Which is a fun comparative metric. We're talking about 2 orders of magnitude. What is the dominant material of the ring? We're not going to add any additional information beyond what you have. What do you know about the world? What is your answer for that? You guys have about a minute left on that question. It does shrink. The question is, how much does it shrink due to that cooling process? Thermal expansion is the terminology. Man, and I love that math does go into building these things. I'm betting big on this one because I'm confident. Absolutely, let's do it. Might as well. What do you have to lose? Some standard internet units. All right, 10 seconds left. Get your answers in now. If you're not familiar, click that predict button and pick one of the 2 options. Again, it's just for pride on this channel. You're not losing or gaining anything beyond points that you can use to make us take a drink, or you can, I don't know, ask a factoid, unlock emotes, whatever it might be. Gotta assume it's anti-shrink material. Maybe. You good on drink?
Yeah, I'm okay. Oh. Forgot I'm supposed to be playing.
So of the games you've played thus far, which one has been most fun, has been easiest?
Definitely Mario Kart is the easiest. I do think Good Job is most fun. I mean, it's, as you saw, it's hard. Like, you do actually have to kind of think about what the game is trying to get you to do. But it's very fun. Because even when you're screwing up, it's like, okay, because it's funny and you're costing the company money.
It's entertaining. And you get a quantity for how bad you screw up. You get a numerical representation. All right, Rachel, how much does the 27-kilometer LHC shrink when you cool it down with liquid helium and liquid nitrogen? Is it 8 centimeters or 80 meters?
80 meters.
80 meters. That is insane. That is the...
Yep, it is. Gets very cold. It's made of metal. There are bellows connecting different pieces to allow for this to happen when the cooldown happens. And of course, the cooldown doesn't happen, in 5 minutes. It's done in a slow, controlled manner for exactly this reason.
Yeah, if you did it too
and many
fast.
others. You're also bringing these really high-powered. Well, I guess you bring them to the superconducting temperature and then you power them. But yeah, and you mentioned 4 Kelvin. It's actually even colder than 4 Kelvin.
Oh, wow.
I want to say it's
like 2 Kelvin or something.
1 or 2, yeah. Yeah, maybe 2 Kelvin.
And I mean, so when you think about this, that's 80 meters in terms of the perimeter.
Yeah, so it's 27 kilometer. Like 80 meters on 27 kilometers is like small, but it's like, when you think about it.
So collectively, I guess somebody could do that calculation, but what is that?
Yeah.
That's like a couple centimeters in across the entire radius.
Yeah, it's a few centimeters per meter or something, so it's reasonable. It's just that it's so long that...
Jeez,
yeah.
That is crazy. Is the darn thing on wheels or what? It's not quite that much. Heck of an engineering feat, absolutely. Across, I mean, to get something that big to measure that accurately and controlled. Oh no, you lost quarters. I gotta give you new quarters.
Oh.
You ran out of quarters. Man, that's pretty incredible. I have a reference point based solely on the answer to bar trivia question I heard like 10 years ago. That's awesome. That's such an awesome factoid. I'm going to remember that one for a long time. Average McDonald's seater. Yo, Ken, just found out I have COVID and will not be in recitation tomorrow. Could you explain IMFs to me like I'm an idiot?
One of your students?
Yes.
Oh, no.
Sorry you have COVID. IMFs is intermolecular forces. So like ion-ion, dipole-dipole, instantaneous
I was
dipole.
just teaching my students, so we don't go over chemistry of dipoles, but I was just explaining like the electric field of a dipole and how it's really important to do multipolar expansions because so many things, their chemistry or their interactions are governed by like interaction between dipoles.
Yeah.
And then in nuclear physics, you know, the I guess looking at the I don't know, multipole moments or whatever of the nucleus teaches you about the shape of the, you know, how the protons are distributed in it.
Mm. Yeah, I try to give that general, like polarity is a universal thing. Like
Yeah.
two electric plates, there's polarity. If there's distance and charge, it has polarity associated with it. So, yeah, but no, I won't explain on stream IMFs, especially since you have a YouTube channel that has all my pre-class lectures.
Oh, wow.
Yeah, so my Gen Chem teachings format is active learning, so they have like a 10 to 20 minute pre-class video that's like nuts and bolts. And then at the start of class, I do a semi-review of that content, but also like context bits, like why do intermolecular forces matter? Why do you have, fat-soluble drugs that you deliver to the body? And then...
do you show them the video, or they're supposed to have to already have
Yeah,
seen it?
they will have to have watched the video ahead of time. Then I reinforce it with the lecture in class, which is slightly different but covers the same things. And then we do clicker questions the rest of the time. So yeah.
I like that.
Yeah, so check out the YouTube channel. I can send you guys a link if you want to learn some general chemistry. The nice part about the videos is I only had to record them once. And they're up there forever. There we go. All right, if you guys want to see all of my General Chemistry 2 lectures, here's a link right there. So you guys can learn all about intermolecular forces and phase transitions and phase diagrams and all sorts of fun stuff. Cherry cheated. That's awesome.
Thank you.
But yeah, best of luck, average McDonald's Cedar. Hopefully COVID isn't hitting you too hard. We just learned vaccines in Florida don't matter, so no one's sick. It'll be fine. Oh man! All right, Misadventures in Astro. Following up on the ring shrinking during the cooling process. Something Sabine's criticisms miss is the engineering that goes into practically building this stuff.
Yes.
Yeah, like the knowledge that's gained from it. I mean, I'm sure something about that cooling system is applied to MRIs that are in hospitals everywhere. Like, general knowledge is gained in these big projects. So I agree.
Absolutely. It doesn't, there is a bit of a, I'm going to stop for a second. Should you, should you build an instrument only because you think you know what you're looking for? Mm-hmm. Or should you just build the best instrument you can and like see what you see? You know, maybe Galileo would have said the latter. Like, just build the best telescope you can. I guess there were some things that Webb targeted, the James Webb Telescope targeted, but really it's just an awesome instrument, right? It puts an enormous amount of like infrared capability that just didn't exist before, and like it turns out it can see amazing stuff. So when something is expensive and there is an opportunity cost, if there is an opportunity cost to other science, the question is worth asking. Should we just build the instrument like just for the sake of saying we built it? But the LHC colliders in general have so much potential positive that I sort of think it outweighs the negative. To build it, even if you kind of think the physics case is not as strong as, say, the LHC was, where we knew we would basically discover the Higgs or something like it. There's some thinking about this right now about the next generation colliders, if there will even be one. And one of the interesting ideas on the market, and it's been as an idea tossed around for a long time, since maybe the late 80s, late 90s, I'm not sure. Might have to stop to have this conversation.
Yeah, no worries.
Which is the idea of a muon collider, that you could get a lot of the interesting benefits of colliding electrons from colliding muons. They're elementary particles, unlike protons. And so if you collide two of them at, let's say each one is 1 TeV, 1 tera electron volt in energy, you will get 2 tera electron volts, fully in the center of mass. So there's all of their initial energy is available to the collision. That's not true of a proton, which a proton is like a bag of quarks. And there's a lot of energy just in keeping the quarks bound up in the proton. And so when you collide 7 TeV protons, you really are colliding much lower energy quarks or gluons. And so you don't get the full energy. So to collide muons, you would get that. And why we don't only collide electrons is because electrons radiate. Probably, does this come up in chemistry?
We don't,
okay,
yeah,
but electrons that are moving in a circle are always accelerating, and so they're always radiating. And so just by the time you get to practically, the kinds of energies we want to access right now, the power bill is way too high because they're just radiating away all this power. So that's why we go to protons. They don't radiate as much because they're much lower mass, higher mass, excuse me. So muons are they also are much higher mass. They're not quite as heavy as a proton, but they're much more massive than an electron. So even if at this moment there isn't a super what would be called like a no-lose theorem for building a new collider. There's some new particle, new physics we know is out there. It might be cool to build a muon collider just to say that you did it, and like best all those challenges, of which there are many, right? Yeah. It is not a shovel-ready type project. It requires a lot of technical R&D to do. And so a lot of people in the community are kind of getting interested around this. But it's not at all I think research at a low level will continue on it, but it's by no means a set project. Oh boy.
I like it.
Are we ready to NARC?
We are ready to NARC. It is time, ladies and gentlemen. Rachel's been waiting 4 years for this moment. All right, those of you not familiar with the stream, we close every single stream by me forcing my guests to play NARC, and we time how fast they beat the game. But don't worry, they have infinite bullets, infinite rockets, infinite lives. They will beat the game. It's just a question of how long it takes and if they need a little assistance at the end. But we have the cartridge because Rachel needs to know the lore behind this game. And so, the tagline, NARC, no one had the guts until now. Which is you. You have the guts. You are Max Force. Your mission: bust Mr. Big and destroy his dreaded criminal empire. Seize all contraband, stolen money, illegal weapons, use rocket bombs, high-powered machine guns, apprehend all suspects, protect the innocent, punish the guilty, stop at nothing. So, ladies and gentlemen, we are going to win the war on drugs, and we are going to start with this.
Oh, yeah.
The Crippler controller, the original NES controller. Oh, Rachel, are you ready?
Yeah, I do have to write a few things
tomorrow. No, you don't. You need to win the war on drugs. This is more important. So go ahead and press start.
Okay.
All right. As soon as you hit the ground, remember the goal is to go right, walk fast as you can.
Have I... Oh, here.
Now you have control. All right, go right, find a door, go through the door. Let's find out. Lori has a question. What was your original time? Do you remember? No advantage in killing. Just go right, find a door. I guess there is an advantage. They slow you down when they shoot you.
My original time at this, I'm going to guess it was 20 minutes.
Let's take a look. We can do a prediction on that, but I want to do some of the other ones first. Rachel Yohay. The answer is 36 minutes.
Here you go.
So, if you can beat 36 minutes, we will consider this one a victory. So, walk right, find a door, walk right, find a door. We're going to do that key card eventually.
Oh, it says press start to play. Am I doing it right?
No, that's not player two.
Okay.
You're going to do player.
Okay.
Also, fun foreshadowing to anyone that's going to stick around for the November 5th stream. Eugene DePrince is going to be host. I'm going to be guest, and we're going to do some two-player NARC speed runs. So we're going to try to beat NARC, get a two-player speed run record. If he practices, we might be able to do a record on stream, which would be really fun. But yeah, if you beat 38 minutes, we're going to call it a victory. But also, we're doing this for fun. So let's see how this unfolds. All right, catching up on a few comments. Non-dairy neutrino had to follow up on the dipole, multipole expansion discussion. My undergraduate research was numerically modeling quadrupole interactions of ultra-cold rigid motor molecules, Bose-Einstein condensates. Turns out there's a second-order phase transition between liquid crystals like states that are driven by the battle between the strengths of the intermolecular interactions and externally applied gradient electric fields. That is fun.
That's awesome.
Stuff in fields, yeah. That's how your liquid crystal displays work. So go right, and you're gonna find you're gonna have to shoot these guys wearing black with a bullet at close range, and one of them will drop a blue card eventually. So yeah, holding A is bullets, tapping A is rockets.
Oh, is that it?
No, that's money from drugs.
Oh, right. I definitely want to take that to be a true top of the 80s.
Exactly. So you're going to shoot the guys in black with bullets somewhere in this range.
Oh, I see.
So hold A. Shoot those guys right over here.
These two. Okay.
Eventually, one of them will drop a blue card. This is RNG. It's like a 1 in 8 chance or something like that. So kind of out of your control, but we'll leave it to the gods of video games. There we go. Blue card. All right. Put it in the slot.
How do I do it?
Pick it up. You should be able to walk over it.
Oh.
Physics. To the right a little bit.
Oh. Okay.
Yes, hitboxes are hard.
And now I go to exit.
Very cool non-dairy neutrino. Yeah, hit the slot, go through the door, and level 2 is officially done. All right, Contra has a particle accelerator question. Do you have to run like multiple computers with really high cycle rates that are staggered by tiny fractions of a second in the hopes that you catch a cycle to frame at the right time? You said kilohertz, right? That was the rate of acquisition. So go
right. Right. So it doesn't work like taking picture. It sort of works like taking pictures. We don't kind of guess when the interaction will happen. The data acquisition knows when the interaction has happened because it's timed in with the beam.
So you're gonna jump in that car.
Oh yeah.
So tap B. There you go. Oh. No, you were in.
Was I in?
Yep. So a little gentler on the push. Just like a little tap. There you go. All right. Stay on the bottom. Go right. Lori, redeem, take a drink. Cheers. We're drinking and driving in NARC because we crashed in the walls.
Oh.
Rachel, cheers. Thank you for joining me for Ask a Scientist Gaming Media.
Sure,
expert science.
Anytime. I'm happy to bring the mediocre gameplay.
Absolutely. It's why we do what we do. Occasionally we get to do this. Man, speaking of which, so it's been 4 years since you've been on the stream. You are now associate professor. You got promotion.
Yes.
Congratulations.
Thank you.
All the pressure's off. Now the administrative duties come in.
Am I supposed to
Yeah, jump over it. Tap B.
Oh yeah. Okay. Okay. Yeah, I've been spared that so far.
Yeah.
But I haven't. I guess I won't be spared it forever.
Yeah, it's inevitable. The Contra. I think it's fitting that the game collision isn't working so well right now for the particle doctor.
Right. Right. Exactly. Yeah, I am.
So tap
never
B.
been B. Yes. Come on.
So you're pressing it a little too hard or too long. Gentler. Just a little. There you go. All right.
Okay.
Physics. That's my favorite part of this game. All right. Old Man Felonious. I know the Atlas experiment has a live collisions visualizer on the website, and the sonifier where you can hear them. Oh, that's fun. Does CMS have something like that?
That is pretty
some
cool.
visualizer to point interested folks if they're curious. That's a fun, just like cool to look at.
Can I get?
Yes. So press both buttons down. Yep. There you go.
Oh.
Take that.
Oh. Oof. And I can't run. I can only walk.
Yep, you can only saunter at that pace.
Okay.
The hip and shoulder action really tied together.
Oh yeah, here we go.
There's no sound. What is going on? Yeah, as other people hear us. From my end, it looks like there's sound. So hopefully you're hearing
Maybe
something.
that I didn't say anything. The question was about. Now I'm forgetting. Question.
A visualizer.
Ah, yes.
Live collision. So tap it. One way to do this, you
There
might
we
put
go.
it down and like piano tap it. So stay at the bottom, then go to the top. Keep going right. Then you'll hit a wall. Then you'll keep walking. Saunter. Yeah,
we
the
go.
visualizer.
Not off the top of my head, I would be surprised. I don't think we have this sonic thing. I kind of remember when they started releasing that. Atlas has really good outreach things. There is something cool I can recommend is you can kind of follow the LHC in real time on the LHC page 1. So you can see like the state of the accelerator. Yeah, exactly. At all times. So like, let's see what's. Yeah, try that. Just kidding. All right, I've gotten good. There. Try the next one.
Next link.
Down. Yeah, that one. That's got to be it.
That's a PDF. So it might have info on it.
Oh yeah. It looks like that,
Okay.
but it's yeah.
There's a live
get to
website.
it.
Tap B to jump. So
There
there's
we
a
go.
PDF describing that.
And I think there is a CMS page 1. I mean, yeah. Too bad I. Oh, here, the nightclub.
Through that door. Nice.
Yeah.
Car level done.
Maybe after this, I can try to find it. Oh, somebody. Oh no. No, that was what you
I put
put in.
that one,
Okay,
yeah.
okay.
And I like that the fun of like hearing it.
Let's kill this clown.
Just got
Scary.
a vendetta.
Yeah, that's scary. Just kill you
It's a moral
too.
imperative. Alright, go right.
Yeah, well, if I'm gonna go slow, I might as well kill everyone while I'm doing it.
Exactly.
I'm gonna saunter
There's
around.
more than one way to win the war on drugs. Just
Yeah.
keep going.
I don't have a good answer, a good link, off the top of my head.
That's cool that Atlas has that. I mean, it's not useful, right? The live collisions or the sound.
I think it's cool. Like this LHC page 1, we're having a little trouble finding right now, but I think it's neat to see the status of the LHC. You can see whether the level of the magnetic field of the dipoles to see whether it's ramping up and actually. Oh, I gotta go to the exit. Bending the paths of particles. You can see the energy. You can see whether it's colliding, whether it's doing commissioning stuff.
So you're gonna grab that card and go up, but don't press up too much. You're gonna go through that door, but just get through the door, and then press left when you get out. Oh, okay. Yeah, I'll have to do that again. Yeah, unfortunately, it lines you up with the door. What's it doing though? So
Is this
I guess
the door?
that's- No, it's the
No,
one
it's
on the
the
end.
next one.
Keep going. Yeah, sorry I couldn't find that link. It should have been the first thing that popped up.
Yeah, I hope it hasn't been put behind some kind of
Oh no.
like.
Alright, shoot a rocket at
Oh,
no.
I have to go left or right when I go through.
So go through, but don't press up after you go through the door.
Okay,
And you can blast these guys with rockets and they'll all
right. Oh,
tap A. There you go. Alright. They'll come back though. They always do.
all right.
Left key card, see that slot right there? Then you go through the door.
Key card.
You
Oh.
back this way. That right there.
Oh.
Yep. All right, we have about, I don't know, 18 minutes left in the stream, at least till 11 o'clock, or whenever Rachel beats the
Could be a
Mr. Big
while.
wins the war on drugs.
Could be a while.
We'll
Grab
see.
another drink.
Last time was 36 minutes. This time, we'll see what happens. We'll do a prediction pretty soon. We should pop one up because we have a couple more that we can do. But if you guys have any last-minute questions you want to ask Rachel, put those in chat. We're happy to answer those while she's trying to win the war on drugs. Also, time's getting short. If you guys have suggestions on anyone we should raid, Feel free to throw those in chat. We'll check it out. Typically, we rate education-related streamers. We're happy to take a look at others as well. So you're going to go left, and you have to shoot this Rambo-looking guy with bullets. And so it's going to be holding A. You're going to do it at close range. Go back that way. So you don't want to shoot him off the screen, because for whatever reason, the card won't drop if you do. There's rules. Physics. We blame physics on all this. So kill that guy to the right. And turn around, and then do that again.
Oh.
So you'll kill this one, and then you'll turn around. And eventually, go back the other way. Eventually, so yeah, holding A. Turn back the other way. Shoot this one.
I really have to get close to him.
Yep, it has to be reasonable range. Yeah, you can go back the other way and shoot again. But it has to be like, there you go, green card. All right. 12 minutes, solid pace. Mahoodles and science are on, awesome. I apologize if I missed any questions. There was a bunch of discussion, lively discussion going on in chat while we were troubleshooting, transitioning the game.
Thank you to the audience for some interesting questions.
Yeah, no,
interesting discussion. We have some real experts in the audience.
Yeah.
Could probably maybe they can come on and play the game better than me.
Nope, mediocre gameplay is required. We cannot do expert gameplay on this, only expert science. So thank you all, but we do appreciate the questions. They are pretty spectacular. All right, do I have any questions I've added since the last time you were on? Maybe the one, so if you were hosting Ask a Scientist Gaming and you could have any guest you wanted on stream to play games, talk science, anyone living, dead, whatever, who would you have on?
Oh. No. Okay, I may need some help about what I'm supposed to do here before I...
Oh, through the door. Sorry.
Oh, okay. To play video games and talk about science. I'm thinking that
they don't have to be good at video games. It just has to be fun to hang out, drink, and play video games and talk science.
I think Robert Wilson, the founder of Fermilab, might be an interesting one.
That's fun. Follow up. What game would he play?
What game would he play? Well, he probably wouldn't know.
Right.
This way. I was just having fun killing these guys.
You're making the most of it. You have the card already. Go ahead and hit the slot. Perfect.
He would play, I really don't know what he would play, but I'll think of something that would be funny to watch him play, which is a game that always made me laugh. I think it's Teenage Mutant Ninja Turtles, where you just like bash on the things.
Yeah. Teenage Mutant Ninja Turtles 2, absolutely.
Yeah. Or
that'd be good.
Mortal
blue card. Mortal
Kombat. I mean, just seeing like a famous scientist play any game like that would be pretty cool. Actually, Marie Curie. I'd like to see Marie Curie play Mortal Kombat. I'd like to see what she would think of it. I think she would kind of like getting I think you'd see another side of her.
She had to have been a ruthless human being, right?
Yeah.
To survive in that world and be as successful as she was.
Yeah.
No, there was some cutthroat.
You're talking about the cutthroat science, the sexism, or the cancer.
Yep. All that combines to make a great Mortal Kombat player. It's what we're claiming tonight. She'd play as Reptile? Oh man, I don't know. I'm gonna say Katana.
Right.
I think she would go with the female representation and be a badass in it. But
is the dog my friend?
I should probably add that. No, you go right. You're gonna come across a guy in a wheelchair and you got to shoot him with rockets. But in the meantime, if you guys want to distract, now you can ask those questions. Non-dairy neutrino. Well, we can't leave without answering the most important question. What's your favorite particle?
Ooh.
Careful, all the particles are listening. So.
I'm gonna say it's the it's the toughest particle. It's the crappiest particle, but it's the one I've been, in my recent career, working the most with.
Kill the guys on screen and then he'll come back.
The tau lepton.
Tau lepton.
The tau lepton is... It's a lepton, like the electron and the muon. So the electron is absolutely stable because of conservation laws, because it's the lightest electromagnetically interacting particle. The muon is stable, like, for all intents and purposes in a lot of cases, because it's very, very long-lived, and it's often moving relativistically, and so it just can travel for hundreds of meters without decaying. The tau lepton is not stable. It's going to decay almost immediately after being produced. So it's very hard to detect. It has to detect partly to neutrinos, so you're going to lose a lot of its...
Back over here. I'll give you a hint. Stay in this area. Gives you a better chance of hitting him. And then kill those guys on screen just because they'll come back. Alright, so now rockets.
Am I doing
So
rockets?
tap. Nope, that's bullets.
Oh. Tap
So
A?
yeah, when he gets back on screen, you have to tap A.
Okay.
Oh, there you go. It's so close. Who knew a wheelchair guy would be so fast? Alright, now you have to go back, kill a bunch of people, he'll come back again. Don't worry, you only have to do this 3 times. Oh, there we go.
God.
He's back. Rocket Pro, you are delivering on the rocket, so.
Oh, this is...
Oh, there we go. That's
Finally.
One.
This is what it's like. Yeah. Bringing 2 beams into collision. Oh, how do I,
You have to hit him 2 more times.
Oh, no.
To kill the guys on screen. Oh, it's fine. You're only 17 minutes in right now.
Yeah, this
You
is
are gonna
what it's
beat your
like.
time.
Bringing 2 beams into collision. Early particle physics experiments were 1 beam and then a target. And the target can be like some huge stationary thing, and but you can't reach as high energies that way. But to bring 2, like, it's really like this, me and this guy. You have to have very good control.
Yeah. Go up here, somewhere in the middle of this.
Yeah.
Kill those guys on the screen. Leo Oz has a science question. What would you suggest is the best future for CERN? Developments, change of purpose? You had to make a decision on CERN. So up this way, past the photo, somewhere over here, he'll show up again. There you go. Nice! That's another one. All right, 2. We need 1 more. All right, best future for CERN.
CERN should build another collider. That's its best
Not his
feature.
turn. That way.
Yeah. I think it's its core mission. It's what it knows best lately. It's one of the only places in the world that can do it, that can keep that knowledge alive. So
Just go over this way.
from a...
Nice.
Yes,
So he's
I
gonna
did it.
stay left.
Okay.
Left. He's gonna drop a card.
Don't make me.
Nope. Stay over there.
Oh.
There it is.
Yes.
If that went off screen, you'd actually be frozen and couldn't beat the game.
Really?
Yep. If that card goes off screen, you're dead. All right. We beat phase 1 of Mr. Big. Do you remember phase 2?
No.
You will. It's coming. All right. You're gonna go to the top of the screen, and you have to do a jump rocket. So it's tapping B and then tapping A. So top of the screen, jump rocket. You got to hit him in the hat.
Oh, right.
So B and then A. Yeah, mashing buttons is not a bad strategy on this one. But generally, you want to walk away from a little bit, get some distance, and then do it. All right, last minute questions for Rachel. Again, suggestions on who we should rate. The Hoodles is on, which is probably a good one. We regularly visit. I don't think the space is available to make another collider. Ooh, interesting.
Yeah, maybe, well, a muon collider would fit almost on the CERN site. That's another...
Interesting.
I feel like I am tapping DNA, but
Yeah, so get away from him. Oh, there you go. Okay, rocket to the face.
Oh, to the face. I thought you said to the hat.
You already got the hat one.
Oh, okay.
So now it's just a rocket to the face. So get some distance. There we go. Contra said resurrect the Texas Collider. So get some distance. Turn around, shoot rockets. Get a little more distance. Its hitboxes are weird. You're getting the right hits. I think you're too close. Oh my god. Get to the top of the screen. That might be easier. And run away. Further to the top. That won't hit you if you're up there. Yep. Let's get some distance. Turn around. Muon Collider is totally new technology.
Yeah.
Alright, now turn around and rocket to the face. Oh.
Am I A?
No, there's a couple rockets coming out. Basically, so get to the top. Get distance away from them. And you can get them off screen completely. Alright, run. Iframes, go right. Okay, now turn around. Don't walk towards them, just rockets. Because if you get too close, it doesn't work for some reason. Alright, now stop, rocket. There you go.
Come on! Come on!
Oh man. Come on. Oh no! This is crazy. I don't know why this hasn't worked yet. This should have hit at some point. Leo Oz said, very expensive, not that much benefit from a Muon Collider. Agree or disagree?
Well, it has to be compared to its competitive technology, which would be a much higher energy proton-proton collider.
Oh, there we go. All right, run away. And we're going to do bullets from now on. So it's going to be holding A, but run away, get some distance. And so when his head goes down, you're going to shoot, turn back. Yeah, so yeah, holding bullets when the head goes down. So holding A. All right, run the other way. Get some distance. Your pace is off right now, and you're doing this without help. So the hard part's done. So get away. Don't run back at him. Let him come to you. Just turn around, hold A button. Let him jump. There you go. 2 vertebrae. Run away.
God, I never knew how hard it was to be a cop.
But don't worry, I learned this through scientific method. All right, run away. And one thing I'd do while shooting him like that is just move up and down a little bit.
Okay.
So turn around, hold bullets now. And then when he gets on screen, yep, just a little bit up and down motion. And down. There you go, another vertebrae. Holy crap, we got one left, ladies and gentlemen. We are on pace for a record time, at least for Rachel Yohay. And no asterisks this time. She's legit beating this alone. Congratulations, 4 years of gaming experience has paid off.
Oh
We're
my
doing it.
gosh.
All right, move up and down some hold A bullets. Run away. Get some distance. All right, there's probably good. Just turn around, hold A. Just move up and down a little bit as it comes in. There you go. Boom, done. Go right.
Oh, there's more?
Well, you got to finish the level, and then there's one more after this, but the hard part is done. Holy crap, ladies and gentlemen, this is going to be good. Get the gold card. Hold right. As the 80s cop movie, we are going to do civil forfeiture of the level, but you're going to walk right. Go as quick as you can. We're going to get to the door. It's exciting. "24 minutes and 32 seconds. You killed it. That was 14 minutes faster, and you did it without any support at all. That was a very solid time. I think that puts you in the top 50, actually.
The NARC training mission.
Yeah. Contact your local DE agent, and you get to put your initials in. It's immortalized till I close this game.
There is the physics case for a high energy proton collider and a muon collider are very similar. But the interesting, I don't know, technological challenges or breakthroughs that could be realized are potentially higher with a muon collider. So we were talking, sometimes you think of maybe not science, but academics as we have to like preserve the knowledge for the future generations. You know, CERN hosting a big collider is kind of like that. And a muon collider would be a significant technological milestone. But, so I think the question is, will we build a sort of 10 TeV, you know, a collider at that energy scale at all? if we decide we want to do one at all, I guess I go to end.
Yep. There it is. Congratulations.
If we want to do one at all, I don't think it's a bad idea. If we don't do one, well, that's different.
All right, but you'd advocate for a muon collider.
I would advocate for it, yeah.
It's a reasonably cost-effective way to.
No, it's not cost effective. I mean,
more so than the LHC.
It's completely. No one's done it. It's not shovel ready, but neither is its competitor idea. None of them are shovel ready. These are decades in the future.
That's
so
fair.
we have to start thinking about it now.
All right, awesome. Well, we just crossed 11 o'clock. Perfect timing. New personal best, 24 minutes and 32 seconds. Congratulations, Rachel. You are on the scoreboard with an amazing time, actually. No support, no asterisks associated with that. So congratulations. Won the war on drugs. We beat a couple levels and good job. Won some races in Mario Kart. Played a little bit of Pac-Man. Pretty good night of gaming, if I do say so myself.
And some great audience participation.
Exactly. No, you guys were super excited about particle physics, particularly neutrinos, but we'll forgive that. But anyway, Rachel, thank you for joining me. It's been awesome. I mean, it's exciting to hear what you're up to and what you're interested in, especially 4 years later, because time flies when you're having fun doing science. But yeah, congratulations on the gameplay. Thank you for joining. Any parting words for the audience?
If you're studying science, get over that COVID, come back to class.
Exactly.
Stick with it. It's awesome. Yeah, parting words are keep up your studies and keep up your interest in all things physics, chemistry, science, because better living through chemistry. I think that's how we started this conversation.
Yeah. Well, no, and then one of the main reasons I love running this stream is I get to learn so much from other experts, like the LHC expands 80 meters when it's cooled down or contracts 80
Shrinks,
meters.
yeah.
That's incredible. A whole bunch of things learned during the night. So thank you, Rachel. I really appreciate it. Thank you for joining me, especially so early in the semester. Yeah, thank you all for joining us for the stream. Our next guest, it'll actually be 3 weeks from now. So September 24th, Marcos Vasconcelos, I think is how you say his last name. He's in electrical and computer engineering. And so he does big data processing, multi-scale robotic networks and game theory, also multi-agent optimizations and distributed machine learning. And he applies that to things like biology and systems biology, which is pretty fun. And so note, that'll be 3 weeks from now. I know we try to do every 2 weeks, but it turns out next week I'm going to be in Sweden for a defense. Week after, I have a test in general chemistry. But after that, we will be here every 2 weeks throughout until it's like December 18th or something like that. You guys can check out the schedule. Actually, I can post the schedule right now because it's on our screen. You guys can see it's a nice mix of people. We got some computer engineering. Ooh, that didn't paste well. Philosophy of science, somebody from philosophy department, which is kind of fun. Cognitive neuroscience. I'll talk about graduate admissions on November 5th. Lisa's from social work, the College of Social Work. And then Fernando's on. Actually,
That'll be exciting.
Quantum field theory. He's a theoretical particle physicist. And so that'll be fun. And then Rashida Harbrook will talk about developmental psychology. I think she does research in things like ADHD. So it should be a fun semester of guests. So yeah, check us out. We'll be back in 3 weeks. That'll be September 24th. Right now we're going to figure out somebody to raid. So stick around. We'll bring our don't drink cans on stream.
Must be too loud.
No, it turns out it's actually okay to drink on Twitch stream. I looked at their formal rules before doing this.
Oh, like in advertising or something?
No, it's like as long as you're not getting too drunk on stream, it is acceptable to drink alcohol on stream.
Oh, okay.
So, yeah. Okay. Leos, thank you for looking out for our interest, but cheers, we do drink. In fact, we have an emote for take a drink, so ethanol. We do on stream, but thank you for the insights. Stick around. We're going to raid somebody education related, but yeah, hopefully we'll see you guys back in 3 weeks when we talk about big data processing and computers and computer science. So thank you all, and we'll see you guys in 3 weeks.